Okay.
Okay, so start now. Okay, so I think it works now. It's 9:05. I think we should start to this winter school. I would like to maybe welcome everybody from all countries over the world, and because we've been quite surprised this winter school was quite a success because it is of interest, I think, for many people. We have over 170 registration to attend this winter school, these webinars. I hope it's going well for everybody. And I would like first to welcome you and to be very thankful for your interest to participate to this winter school. Due to this success, we were not expecting maybe all these people from all the countries, so we had to adapt from. We previously think about making a Zoom meeting with something like maybe 30 to 50 people, but because you were too numerous, we have to go through a YouTube channel in order making everybody be able to attend these practicals and this winter school. So these have some implication in terms of technical issues. So there will be a delay between when we are speaking and when you are watching all our slides. So there are something like 20 seconds delay, which is not really appropriate to a live chat. But I think we will adapt and try to collect most of your questions through the chat of the YouTube. And we will try to make some short breaks of a few minutes in order to collect all your questions and try to answer these questions maybe a few seconds after you write this question on the chat. So the objective of this winter school is to provide some insights and tools for landscape characterization, and from habitat mappings, landscape connectivity mapping, and ecosystem services assessment. So it is quite ambitious, but I think we can just give you a broad overview about the advances and outcomes of one project we are involved in, which is the ALICE project that is supported from the European Union INRAe program. And the idea of this winter school is to give you some tools to do this landscape characterization. And these tools, of course, are not maybe the most appropriate ones, but there are some quite advanced ones that could be of interest for your own work. And we try to provide you some data sets and practicals in order that you will be able to replicate these methods to your own case studies. And we won't be exhaustive in terms of methods, of course, but we will give you some of the advanced methods to do that. So let's go through this introduction, and let just give us you to provide you what we are talking. What about what we are talking about landscapes? Okay, so this is a landscape, which is an agropastoral landscape located in mountains somewhere in Europe. And when you are looking at these landscapes, some of you maybe are observing some kind of land covers. So you can see there are some meadows, there are some forests, some of them are deciduous forests or coniferous forests. And there are processes of encroachment. So this is a landscape as seen as land covers. But also you can consider this landscape as land uses. And sometimes it could be like silvicultural land uses, agropastoral land uses, but also a non-land use, which is the abandonment of this land. But of course, you can consider as well landscape as functions and ecosystem services in terms of habitats. For example, meadows could be habitat for a specific species. It could be also an approach as cultural heritage, because you can see there are some old houses dedicated to agropastoral practices. There are also some trails that are dedicated to recreationals. And your encroachment that could be a service to limit the erosion of the soils and also to provide some diversity in terms of habitats. But of course, landscapes are provisioning some services like wood provisionings, agricultural provision as well. And between these different elements of the landscapes, there are some connectivity, some functions that are very important to consider in order to do some landscape management. So we can define the landscape as the result and support of natural and anthropogenic interactions, legacies, and sustainability. So today we face some big challenge about how to deal with the landscape management, how to be sure that all our policies today are appropriate to make a sustainable development of these landscapes. And it is very important to consider this in order to define very helpful and strategies and policies for the future generation of humans. So we face the challenge of making a good assessment of the landscape usefulness for people today, but also we will face the challenge of defining sustainable policies into the future. Okay, so the idea behind the INRAe project is also to consider the BGENS. What we call BGENS is the blue and green infrastructure network. It means that it helps to define the functionalities of connectivity between patches of landscape that have some functions for some species, for instance, and they are dispersed all over the landscape within what we call the landscape matrix. And the idea of ALICE is to try to assess if the blue and green infrastructure network can be a landscape management tool to optimize and improve the ecosystem services, but not only the biodiversity connectivity. To do so, we use 4 case studies, our experiments in terms of assessment of this implementation of BGENS. And the 4 case studies are located along the Atlantic area of the European Union. And we have 1 case study in Northern Ireland, 1 in Brittany, and 1 in Spain, in Cantabria, and another 1 in Portugal. The objective of the ALICE project is to define, to go towards the better management of the Atlantic landscape through the development of tools to characterize biodiversity and ecosystem services. So I would say that it starts from remote sensing images, try to go through all the process of production of maps, which could be land cover maps, land use maps, scenarios, ecosystem services, assessment maps, to provide advices or strategy to define sustainable policies. This project is clearly in line with 2 main science approaches, 2 main paradigms of the landscapes. The first one is the land change science paradigm, which is defined on the left side of the slide. And the second one is in line with the socio-ecological systems and their resilience over time. And there are very good framework to define the ALICE project as a whole. So today we will go through this winter school through different tools in order to provide maps that could define ecosystem services, that could define landscape connectivities, that could define also the habitats of these landscapes. There is another seminar tomorrow morning. If for some people could be of interest, some people are already registered for these two events. It's to talk about how we can consider the landscape dynamics in order to better define these sustainable policies. And in brief, I will go through the production of the basic inputs for all this approach about the production of land cover mapping. So basically, I would say that there is a whole community of scientists, I would say any kind of collectivities that are working on satellite images to provide land cover maps through different kind of methods that belong to the remote sensing classification approach. But it is a critical step because there is some remaining classification errors. All maps are not perfect, of course. And if you are used to these approaches, you have always this kind of kappa coefficients that could be a good accuracy assessment indicators that never reach 100%, meaning that there are, for a kappa of 90%, there is always 10% of error remaining in this map. Of course, this error can provide also some over or underestimation of the land use and land cover changes. So it means that we have to face and to integrate to try to minimize this error at the very beginning. This error can be due to the pixel resolution. And of course, when we go through long time series over the last 30 to 40 years, for instance, the differences between the pixel size of these satellite images can provide this kind of error between the different dates. For instance, when you do a classification, you can see there are sometimes some kind of salt on pepper effect due to misclassification or to confusion between land cover classes. And this salt on pepper effect are not maybe appropriate to do some land use and land cover change analysis. So if we want to improve this classification and to minimize this error, we can use also some additional data that could be some shapefile, what we call some features in this project, in order to try to put all the classification results into this feature landscape polygons in order to remove all this salt and pepper effect. These features could be from the LPIS database, European database, from agricultural plots definitions, but also they can be made from topographical variables. For instance, we can consider the classes of altitude, the classes of orientation aspects and slopes and so on to create homogeneous features that are the same properties. For instance, the same area in mountains located between 2000 and 2001 meters high, exposed face to the east side, and with a gentle slope and so on. It means that all these polygons could be like ecotone definitions of the landscapes. Then, if we apply this approach to different time series of land cover maps, we can also detect some kind of false change and true change. For instance, if you can see here in 1995, you can detect some fallow lands and forests, and there is a confusion because of shadows that urban area could be there. But in the most recent date, we can see that there are bare soil only and fallow land, shrublands around this place. So it means that the shadow in 2010 was an error that can have been corrected thanks to this trend analysis over this time series. So this is this kind of false detection error, and also you can have some true detection change in terms of urban area, because there were no urban in the most recent one, old date, but also in the recent ones, you can see they are some urban here. Then some of you can be also interested to go more into details in the land cover classes. For instance, in this map, we have distinguished what are meadows and what are cropland. But in some cases, for instance, to better assess connectivity between some habitats, maybe you need to go more into details to characterize different crops, like maize, wheat, or other crops, but also to distinguish the different type of meadows, permanent meadows and temporary meadows. And you can use different kind of external data, or you can use satellite time series to go through the whole process to detail this kind of maps. I would say that the more you keep on the left side of this approach, the more generic you will be. The more you will be on the right side, the more need of external data you will be. But what we noticed, thanks to the ALICE project, is that if you want to have a good stakeholder engagement in the whole process of ALICE, of your project, of your landscape management progress, you will need to better specify all these maps, because they will be the maps that the stakeholders are using usually. So this is just an example about all the data sets that have been produced during the ALICE project. So you can see the 4 case studies. So this is the French case study, the Northern Ireland one, the Spanish one, and the Portuguese one. And thanks to this data set, I think now we will be able to jump into the program of the winter school, because this data set will be the basics one that you will use for your practicals. So let me just introduce you shortly the program, but you already know what is the program. I am Thomas Wett from INRAe from France, and I already did the introduction. And then my colleagues will be the next one speakers. And the first one will be José Alvarez from Spain. That will present a tutorial about habitat mapping using remote sensing and in situ data. Boussard from INRAe from France will present you the landscape connectivity tool k.LAB. That is, I think, very useful to characterize the landscape connectivity. And then Stefano Balbi from BC3 from Spain will present the ecosystem services assessment using the k.LAB platform. So I think maybe I will give the floor to José. And if you have any question before starting, I will be happy to answer these questions.
Well, thank you very much, Thomas, for this this introduction that put on the table very well the ALICE objectives and main developments at the level of landscape. I will share my screen. Okay, because we are going to start talking about the habitat mapping, as Thomas explained, going from in situ data to large scale. And in this consecutive content of words of this workshop, on which we mentioned landscape, habitats, ecosystem service, and connectivity. Better said, landscape, habitats, connectivity, and ecosystem service mapping, that are not something that is widespread in the middle of nowhere. but it's something related in the concept of ALICE towards the final development of the blue and green infrastructure network schemes that we aim within the project. When I'm going to tell you a storyline, on which I am going to explain how we use information for going from in situ data to geographical scales when creating habitat maps. I will stop 4 times or a number of times to demonstrate you with hands-on exercises with some colleagues that are expert in the topics that they are going to explain you, that are very like the key steps within the whole process. When we talk about spatial information at the landscape level, it's mandatory at least in the context of Europe to talk about Copernicus program. So the different services of the Copernicus program allow us assessing information about marine, atmospheric, climate change, and so on information. But here we're going to just focus on the land and the Marine Land Monitoring Service that provides us with a large number of services and data and methods that can allow going for specific targets in our projects with very detailed information about different issues. We have within the different approaches of the Marine Land Monitoring Service, since from the pan-European scale to the local scale, we have information about riparian zones, the urban atlas, about detailed information of the coast areas. It's a new project that they started some months ago. Nature 2000, we have the high resolution layers with very valuable information. And we have, following the Eagle scheme, the Korean Land Cover Plus project that will give us briefly the different instances that give us information, advanced information in the way that we are used to manage the Korean project, the Korean land cover. So we need, when talking about habitats, we need this spatial data. And we know that spatial data is not static. That spatial data changes through time, going from past landscapes that we had decades ago, and the drivers, natural and anthropic drivers, changed the landscapes towards what we have now. So we need also not only spatial data, but we need the knowledge about temporal dynamics. This available information that comes from Copernicus or comes from previous projects that are easily available sometimes is not enough for fulfilling our objectives when we work with the distribution of biodiversity, the distribution of vegetation, because they are usually created following vectorial approaches that inform us about static thematic maps that has not the enough thematic resolution that we need, the spatial resolution, the temporal resolution, we cannot update easily. So sometimes, as Thomas explained, we can also take the decision of work directly with our with the satellite information, making a classification of the satellite imageries. So in this case, as Thomas explained, we can work at the pixel level that can afterwards translate into patches, but we can deal with the dynamics of our territory following our classification schemes, defining our own typologies, and using all the powerful of remote sensing, combining satellite and other sources as old aerial photographs, LiDAR, radar, for creating our maps. In this case, we can use the information we have through time, the remote sensing information, for assessing, once we have defined a region, assessing the changes between and or among our land cover types, and making relationships of what occurs, for example, when burning shrublands or burning certain land covers, and how vegetation recover afterwards. Of course, we can make an spatially explicit representation of that changes that give us a knowledge about how landscapes evolve. But again, we go to complex territories as occur here in in the Mediterranean or the European domain, we have very complex territories, very complex land cover patterns from the top of the mountains to the coastlines. That, when talking again with the distribution of vegetation, we're talking about biodiversity, or we're talking about the topic of this presentation about the habitat maps, we have to go in more detail with our in situ data, with our expert criteria for getting our final maps, for afterwards working with our conclusions and application to land management as occurring in ALICE, when we aim developing the blue and green infrastructure schemes that improve the landscape, the landscape functioning and ecosystem services. A good example is the management of information for reporting following the Article 17, the Nature 2000 areas under the Habitat directives. So we need go much more beyond of landscape dynamics, of how landscape change. We have to go into the distribution of vegetation following the scheme of the Annex 1, and the distribution of the habitat types following the scheme of the Annex 1, and not only talking about the distribution, but also about the conservation status, also about how the structure, functioning, the vulnerability that affect that habitat types changes, for finally defining the management plan, local actions for improving the distribution and ecological status of that habitat types. We can face that problem at the regional level, at the local level, more or less, but afterwards we have to extrapolate to whole geographical distributions, to biogeographical distributions. For example, we faced in a project that we developed a couple of years ago in Turkey, on where we have to go in an area that is more or less half of the Iberian Peninsula. And going into the ALICE project, as Thomas told us, we have 4 case studies that on which, even though they are more or less regional scale approaches, not as big as I explained you in this example of Turkey, we have distributed throughout the Atlantic region. And there is a very important thing. We need methods, we need data that is comparable in space. We need to compare the different case studies because we want to understand how drivers of change affect the landscape dynamics, affects the biodiversity distribution. And we need methods that can be repeated continuously, or having a periodicity in time for assessing how the changes affect the distribution of landscape features and affect finally the ecosystem services. During the workshop, I will focus mainly on the Spanish case study. This is an area located in the north, in the region of Cantabria, the eastern part, sorry, of the region of Cantabria, for demonstration during the hands-on how everything that I am going to tell you theoretically with some examples can be done, or is done actually with the programming and GIS methods. So for fixing 3 main steps that we are going to explain during the presentation, we are going to talk about how we use information for creating habitat maps. So we want first to map vegetation patterns. Once we know the distribution of that biodiversity, the distribution of that habitats, we need also to understand how the different parameters about the structure of that vegetation, how vegetation functioning changes. So which are the drivers, the processes that manage that patterns for creating a dynamic of the system, and finally how that dynamic affects the functioning. For once understood, defining reporting and management actions that allow us using that well-established monitoring, creating restoration and conservation actions that preserve biodiversity while improve ecosystem services, as the project ALICE aims. So yes, firstly, focusing on the habitat mapping issue, as I told you, sometimes we're talking about the distribution of vegetation. We cannot use directly really available maps that we can download from somewhere. I talked about Copernicus, but we also can talk about any other development of any project, because we need creating our own schemes, our own analysis. We have our own objectives, and we need to start from in situ data, from expert criteria that can inform us about what we need, but specifically for certain points in space. So here comes the use of remote sensing as a very useful tool with the capability of enlarging our observations from in situ data in a cost-effective manner. But this needs to make some methodological steps that we will try to show you today in this first part of the workshop. This method of remote sensing is not different from the traditional mapping system. In fact, they are complementary tools that need to be put in common. So Copernicus and remote sensing and modeling should not be understood as something that replaces, should be understood as something that improves. So we have our in situ data, and that's what we have. We can photo interpret, we can go more to the field, but we will keep always that. Remote sensing arrives to the mapping, to the habitat mapping world science for improving, for allowing the enlargement in a cost-effective manner of that observations that we make like experts, like botanists, and so on in the field. So they are not something that excludes. It's something that need to be complemented with the traditional, let's say, traditional expert-based mapping system. And the powerful of this, I'm going to explain this, and Anna afterwards will tell us something more about remote sensing. But I would like, hopefully, to spend 1 week talking about Copernicus and remote sensing, but that's not the objective of this talk. But everything is based on the capability of remote sensing, as much as you should know, of watching beyond what we can see with our eyes. So by using the electromagnetic spectrum capabilities within the different bands of the satellites to interpret what do we have through the different spectral signatures of each land cover, of each vegetation type, of each ecological status, have on the reflectances of the responses of the ground with the interaction of the energy that comes from the sun. So these allow us creating the spectral signatures, as Anna will explain a little bit in a while, for working with the data for defining the different land cover types. So once we arrive to this point after this theoretical explanation, we have to start think about what actually matters when creating our habitat maps. So we have information, and we have other information that we don't have, and we have data and methods that we can manage, and we have other things that we will have not still for the moment at hand, so we cannot do everything that we want, but we can do quite a lot of things. So we have to start thinking in a SWOT manner to be able to define the best we can do with our data. So in trying to simplify the approach for habitat mapping, we created these 4 boxes that try to conceptualize, and are the 4 boxes on which we will have some hands-on exercises that will allow you to see how things can be done, for afterwards try to repeat by yourselves with our case studies, with your own data, to repeat the things that we are going to explain you. How we decided not to develop this workshop like exercises on which we step by step all together repeat what we are going to tell you, because we are quite a lot of people. You are almost 200 people registered at least. So we prefer to show you, but you will have a demonstration databases of all Alice case studies that you can download for playing with. And of course, the most important thing is that you will have everything explained step by step that we are going to show you now, for allowing afterwards you to repeat in your at home, working with your own time and methods. So well, we are going to explain you theoretically each of these 4 boxes, and afterwards within each of the boxes you will have a hands-on demonstrative exercise. So for doing our best, so for answering what actually matters, for habitat mapping, we have to define first a classification system. So we need to know what do we want to map. We need to know what do we want to look for when we go to the field. We want to map only forest. We want to map only deciduous versus broadleaf forest. We want to go into detail with the dominant species, with the different genus, Fagus, Quercus, and so on, or we want to go also within the subclassification of each forest type, or we want to go into the different conservation status or structural developments of each subclassification of forest community. So we need to define first a classification system for afterwards define the level of that classification system for mapping our patterns. Then we need occurrence data of what we want to model, what we want to map. We define first the classification system, and then we need occurrence data, in situ data for that thing that we want to map, for training, for validation, our models, our modelizations. Then we need predictor layers. We need information for extrapolating, as I explained you with talking about remote sensing, for extrapolating that observations. And finally, we have to put in common everything with a modeling procedure that will give us an outcome that we'll have to manage afterwards with post-processing analysis, mainly in a GIS environment, for creating our final maps that will allow defining the management actions, making the reporting, and so on. Starting with the classification system, we have many options. I told you before about Nature 2000 reporting following the Article 17 and so on. So we have there the Annex 1 that defines a number of habitats, a number of, let's say, boxes of habitats, because they have not an ecosystem-based approach. They are boxes of things that we have to report, we have to talk about. But for going into detail within that boxes, we, for example, in our work within the Nature 2000 and with our ecosystem monitoring world, we use UNIS classification that allow the experts to define some typologies that can be tracked and can be modeled afterwards, and that follows the list of the Spanish habitats defined from the ministry. This is a hierarchical classification system that can be or should be managed, handled following expert criteria for getting finally homogeneous classification of vegetation, of biodiversity, that will explain much better than me Borja Jiménez Alfaro from the University of Oviedo and the biodiversity mixed unit from the University of Spain, and he's a botanist and very expert person in UNIS and everything that relates to vegetation. So I stop here my presentation and I leave Borja to start talking about this.
So hello everyone. Very nice to be here in this winter school, and I will continue with the explanation about habitat topologies and training data. I would like to start with a report that the European Environmental Agency made a few years ago. And basically what they wanted to do is like to translate all the effort that has been made in vegetation mapping in Europe in the last years to try to see how all this information can be used for habitat mapping. Because you know that probably many of you in Europe, we have like nature conservation targets, which are the European Habitat Directive habitats. But the problem is that in most cases, habitat mapping has been based on vegetation units at different scales and in different regions. So basically, the main aim of this report was to detect how in the future, in Europe at least, we can get better maps that are useful for different purposes, and mainly nature monitoring and habitat mapping. So here you can see a few items about what were the challenges that were that point out in this review. And basically the main point is that we really need to have better maps based on GPS data and based on remote sensing data, so the resulting maps we have can be replicable in the time, and they are much more useful. And this is not exactly the same approach that traditional vegetation mapping has used in the past. So our challenge is to find a way that using some kind of vegetation background, or let's say botanical information, we can define a series of habitat types that then we can model and we can spatially put in a map. So the first question that we have in mind is what to map. What are the real scale of the habitat units we have to use? And in this graph, you see that in general there is a close relationship between the scale of your area and the vegetation unit. I mean the grain of the habitat of vegetation unit that you want to map. So basically, if you are working a very narrow scale, you can map individuals of plants, for example. And if you are in a very large region, typically what you are really mapping, you probably will be like large vegetation units or formations, or maybe you can get some land cover map. But if we want to make the mapping applicable for conservation planning, we need to somehow rely on the good ecosystem types or habitat types that we are concerned about in nature conservation. And so we are somehow like between a vegetation type or a community, because we would like to differentiate different forests because we know they are functionally different, but we know they are also different in species composition, but we cannot go to the details of all single species. So that means that what we really need is to make large scale maps, or let's say regional scaled maps, and to use a vegetation unit or habitat unit that are like, let's say, close to a vegetation type resolution. And this is the main challenge that, according to this graph, is here in this red cycle, because it's, let's say, a gap. So if to deal with that, we need a classification scheme. And I don't know if you are aware that currently there is a global classification of ecosystem types. This is a project founded by Australian colleagues and the IUCN, and they are now producing a global list of ecosystem types that can be comparable across different continents. Something like deciduous temperate forest, for example. Yeah. So the main idea is that under this classification, this provides you some kind of ecosystem types, and that you can compare across different countries, but then you need to go a bit in detail in your region to see how your habitat units match with that. So we have something very similar in Europe, and probably you know about this. This is the UNIS classification. So is the European Information Nature System, and they basically, in the website, this is what you can see here on the right, you can have two, let's say, habitat typologies. First, you have the UNIS classification system, that is really a classification of habitats. And then you also have the Natura 2000 habitat units. And it is important to remark that the real classification of habitats in Europe is the UNIS classification typologies, and not the habitat directive habitats, because they are just a legal instrument. So we are going to map. What we need to focus on in Europe is this UNIS general classification. So I will give you an example. This UNIS classification is a hierarchical system. So let's say you want to define a unit for a forest. We have something that is called first UNIS level, number G, and is defined as woodland, forest, and other woodland. Then we go to the second level. G1 is broad-leaved deciduous woodland, and the third level is, for example, the beech forest of fagus woodland. And then you can go to the fourth level to find exactly you have something regional. Okay. What we found years ago is that at the continental level in Europe, this third level of UNIS classification is quite okay. It's something like more structural, functional, and at the regional level, it's probably not enough to make mapping, but it's good to make comparisons across different countries in Europe. So if you go to the website of UNIS, you also probably will find that there is something called a revised version. This is something that is now going on, and basically the idea was to refine this third level of classification to find something more ecologically understable, okay? But for the moment, this is not complete. It's just to let you know that this is now happening. But I will continue with this 3 and 4th level classification of units to let you understand what are we doing now. So I will do it by 3 case studies. The first one is the mapping of habitat types that we did with Jose and with the IH Institute in Cantabria region in Spain. So basically what we wanted here is to have a relatively quick habitat mapping of Natura 2000 sites. And we used a combination of new field work to collect GPS locations of different habitat types, and also we used traditional vegetation maps from which we collected maps corresponding to our units. The most important point here is that we focused on both units and Natura 2000 habitats. So our target was to map Natura 2000, but what we found is that for doing that, what you need to map first is the UNIS classification. Why? Because with UNIS classification habitat, you have the broad range of habitat types. Some of them are protected and they are part of the Natura 2000 protected habitats, but some of them are not. But if you want a comprehensive habitat mapping, you need to use all units of vegetation or habitat types available in your studied region. That's why we are focusing on the units types. So we made some kind of a methodology to proceed with these maps based on remote sensing. And even if we focused on the Natura 2000 units that you see here in the table, that's when we realized that for getting these resolution, what we needed really is to map the UNIS classification habitat types first. Is what I will explain you now in a different example. This is our case study 2, is for Central Anatolia, Turkey. This was a project for developing a Natura 2000 system in Turkey, and the project wanted to make an example of new habitat mapping in Central Anatolia. That means approximately 1/3 of Turkey, so it's a huge area. And we needed to make a map from scratch. So basically, we didn't have any basic vegetation map or something. And at the beginning, the project wanted to make some kind of traditional mapping, like go to the field and use orthophotos or some aerial image to digitalize in the field and to involve a lot of people in the process. But we did some calculations, and using a traditional mapping, this would cost approximately 100 million euros, and you would need more than 5,000 field workers to do it. So it was something that had no sense, and we decided to go to a more practical view. So we based on field data, which means that we made some kind of training for local experts and botanists. In total, there were 22 field workers. And what we made, it was a systematic field survey over natural areas. And we defined natural areas using the land cover 2012. So that means we defined broad units like forest or open grasslands. And we asked the field workers to make transects by car, just crossing these areas and then collecting GPS points from these areas. So in 2 years, we were able to get 60,000 GPS points, and almost 200,000 map points. That means something that is not really the location of the field worker, but it's something that you can interpret in the landscape. So the main point here is that in 2 years, we were able to collect a lot of field data that then was used for habitat modeling using the remote sensing and topoclimatic variables. But the critical key point here was to define the units to map in the field. So here is when we adapted for the first time this units classification to our region. So our region was Central Anatolia. We started working at the units third level of classification. That means, for example, E12, this is the third level, which is quite common for all Europe. But then we defined the fourth level, which is something adapted to our region. This case was Central Anatolia. So we defined, for example, different types of steppes or different types of woodlands, which are only occurring in Central Anatolia. So that means that this fourth level is unique to our region, but still the third level is comparable with other, in this case, oak woodlands from all of Europe. And we have here the list of all our points. And with this data and using remote sensing variables and the modeling framework that Jose will explain you in the session today, we were able to produce a general map. This is a map of major habitat units in Turkey. The good thing of these maps, here is a multi-classifier map, so it's like some visualization of a traditional map, but you can also map just one single unit, for example. So the main point is that any single of these habitat units can be correlated to a Natura 2000 unit because we have the match between both systems. That means that if we are going to make a complete habitat mapping, we need to use something like units classification types, but then we can always link these units to the Natura 2000 types that are under protection. Some of them are, but some others are not. So just to finish, the case study number 3 is the mapping that we are developing for the Atlantic region in the northwest part of Spain, and part of it is also one of the targets of the ALICE, this ALICE INTERREG project. And here basically what we are doing is to try to calibrate all these methods and to try to find the best habitat typology that we can use for making automatic mapping of habitat types. And everything is explained here in this slide. This is our study area. You see this blue color is the Atlantic Spanish region in the northwest of Spain. So we consider this is like our biogeographical region. And basically what we did is to adapt this UNIS hierarchical classification to a level 4. But this is not the level 4 that you can see in the website of UNIS. This is the level 4 that we adapted to our region. That means this Spanish Atlantic region. So basically we adapted the UNIS classification system to our particular region, developing this 4th level of classification. Sometimes the units we are dealing with are 100% the same of the number 3 you can find in another region. But in other cases, we had to adapt exactly to the ecological properties of these units in our studied region. This is a way to optimize the habitat mapping and modeling. You can see here that some of these units of UNIS are linked to a habitat directive, to the code that is under protection in Europe, but others are not. We have like some acidic fens here, for example, or we have some forests that are not in this list that are forests that are existing in the wild, but they are not protected. But we need to map them anyway. We want to make a good habitat mapping. And you can see also that some of these units corresponding mostly to wetlands, for example, or small habitat types that have very low scale resolution, that they cannot be modeled because simply it is not possible to make a model based on remote systems. So another important point is that all these units we link with JES here means that they are relatively dominant in the landscape and they can model using remote sensing and field sampling, but not all of them, okay? So this is also something important when you want to report the trends of habitat types for Natura 2000, for example. You can approach many of the habitats using habitat mapping and modeling in this way, but some others would need additional fieldwork and additional, let's say, complementary studies. But in any case, most of forests and grasslands and shrublands and major dominant units in the landscape can be modeled. So at the very end, what we have mostly is a field sampling that we are conducting almost every year. So every year we have some botanists in the field that are collecting GPS points corresponding to this classification system. And sometimes we need very good data. We can also go to small vegetation maps made, for example, in national parks or natural areas, and we can collect additional data points from there if they have been done in very big detail. And we mix all this field information and we make some standardization. That means to put all GPS points or all locations under the same habitat typology. You need to conduct some spatial filtering to clean up the data, to reduce the spatial autocorrelation. And at the end, what we have is a set of occurrence data, like locations, accurate locations, which will be our occurrence data for the next step, which is modeling. And it is important to remark that this occurrence data is optimized for our study region and optimized for being interpretable in terms of both the UNIS habitat classification at level 3 and the habitat directive typologies. That means that the final maps that we will get with these occurrence data after modeling could be used in very different ways. So you can use just for reporting ecosystem services of the landscape, or you can use for selecting protected habitats under the Natura 2000 context. And so this occurrence data is what you will have for the study case of Alice in Cantabria, is the one that will be used for modeling in the next steps. So I have ended here. I think that any potential question should be recovered at the end of the whole presentation. So I give back the microphone to Jose. Thank you.
Well, thank you. Thank you very much, Borja. So we have heard a very good explanation of what I wanted to tell you about. We need mapping something that we know we want to map and something that we can interpret and find in the field and translate into our occurrence data. So once we have defined, as Borja perfectly explained, our classification system, and we use UNIS for different reasons, as Borja explained, we need occurrence data. We need something that puts on the table, on the GIS table, the spatialized information of that classification typologies, both in space, I mean, we need to cover the whole study area that we want to map, that we want to monitor, and also in the environmental domain. So we do not only need covering the whole area, but we need covering for each of our classification typologies the whole variation of the gradients, the main abiotic or environmental gradients that we have within our study area, for having information for training, for having information for validation, and for having information of the whole variation of conservation statuses and ecological statuses that we have within each of our classification typologies that we selected. In this case, the UNIS types of vegetation that we selected. So when we want getting this occurrence data, the first resource is going to that Copernicus, to that previous map. Let's use core inland cover as an example. We can go for that map that are easily available and download and create some using simple GIS approaches for generating random points and so on for getting our occurrence data. But what happens is that there is a mismatch within the legends that we have in that really available maps and the legend that we need for creating our habitat mapping approaches. So this approach sometimes has a problem because there are approaches based on landscape features, as we all of us know, Corinne and similar maps, that sometimes the variability within the patches is not suitable at all. And if we go to the field, we will see that some of that locations that were mapped as, let's say, broadleaf forest, maybe are not. The whole patch is not a broadleaf forest. And even though we have not the typology depth enough, we also have not the spatial accuracy enough for dealing with the habitat mapping approaches. So using this map anyway, we can get a large collection of in situ, let's say in situ, of training data used for, useful for modeling. That maybe is not good for, is not useful for mapping, for modeling, but it's useful for some kind of calibration, for controlling that our predictions will be in line with other maps, that official maps as Corinne. In Spain, we have the CIOSE, we have the forestry map with a very high accuracy, and it's like the most official map that talks about forestry. So we have to be in line with these maps. One step beyond, we can use more detailed maps that we create, high scales with more deep typology. Talking about UNIS, we can create our own maps with photo interpretation, going to the field. This is an example of my PhD, on which I was like a couple of years running through the mountains of the northwest of Spain and creating detailed maps at the vegetation level, not detailed legend, but detailed enough for being sure that my points will have no uncertainty, or less uncertainty that if I use other large scale map. So with this information, we are in the middle of the good and the easy. So we have points that maybe that maps is not gathering the classification that we need, but we can just give some information easily that is more or less useful, let's say more or less. We have to use with caution for running our models. But sometimes anyway, we will find the problem that I explained you previously. We will go to our in situ data, and using different approaches, going to the field for the interpretation, or using our GIS variables, as I will explain to you later, we can identify points that are not useful anyway. We have inaccuracies because of the spatial accuracy, the typological accuracy, and so on. So the final resource is the less efficient in terms of human and monetary costs, but is the really useful for running habitat mapping approaches without collecting uncertainty since the beginning, is the going to the field and doing our sampling under expert criteria, as we did, for example, in different projects in the north in our region, included, of course, the ALICE project within the Spanish case study. So we make transects, we use the expert criteria with people that know perfectly what they are doing, talking about the vegetation, the gradients that occupy that vegetation communities for getting a perfect sampling, as we did in Turkey. For example, as Borja explained, this project was a project with funding enough for having a large number of experts in the field. And also when collecting the information, there is another source of uncertainty. We have to take into account that we can go to the field and locate a point in a map. Then we have to translate that point into the GIS environment. And we have an uncertainty of doing that translation if we don't put a lot of attention. So we have digital tools as we use in Turkey, and all of us and most of us use when we go to the field, for having a direct translation and connection through using the cloud capabilities for creating our database with high accuracy. Not only the typological accuracy, but also the spatial accuracy when we locate our points. So with this approach, we have a very useful, very good database of information for training, for validation, and for knowing not only the distribution of the habitat types, because once the botanists go to the field, as Borja explained, they collect also information about the conservation status, about the composition, structure, function, the pressures that that communities are suffering in space, for having a very good database for running our models. In Turkey, as Borja explained, we did this with almost 220,000 points collected in the field, both at GPS position and also with a very reliable definition of what was going on in the field by the botanists. This is not real. It's not a real scenario because it never happens to have these capabilities, but we have to focus on this, covering the whole area and covering the whole gradient, but going to the minimum of points that allow us reaching suitable maps. As Borja also explained, we are following this approach in the north of Spain, in the whole biogeographical region, that now we are more or less in the middle of a project to enlarge this to the whole north of Spain, including also the Pyrenees. So we want to do this, but we, of course, as you can see there in the green dots, we have just a small part of the whole biogeographical region with that field mapping approach, because of course we cannot cover the whole territory, or we have not done still. What we have in the middle of is the in situ data of the autonomous regions, of different projects, a lot of colleagues that we have contacted with many people already, talking about this approach of working together for making habitat maps, for making for assessing the vegetation, biodiversity distribution in the north of Spain. But we have this in the middle quality. That means that there are available maps and other projects that we can use for translate their own classifications, their own maps into our classification typologies, as Borja explained. But once we have this information, we have to work with this data for making a final database for training. And I will show you just briefly, because we have not time enough for going into detail, but at least showing you. I'm going to stop sharing this screen, and I am going to share, yeah, again okay. So I go to my GIS database, on which I'm going to try explaining you easily what do we mean when we talk about, that Borja did as well, filtering our training data. So we have points that come from the field observation of our botanists, with GPS quality, with a detailed explanation of the content of that GPS point, about the distribution of vegetation, which habitat types it is, information about the conservation status. So that's okay. So we have training data that we can here we can classify using the different sources. I'm going to manage this. This one I want to remove. So this information that you can see here in different colors with dots of different colors, doesn't matter the meaning of the different colors, is information that comes from the field workers. We have been, as you can see here in the legend in the GIS, the fieldwork 2019, training from, I kept the original name, is not well structured. I mean, we have a geodatabase with this well structured, but I want to show you where the information comes from scratch. So we have information from different years, 2016, 2017, 2018 is not here, but okay, 19, that come from the field. But we have also, as I told you, we have also information that come from maps. I will put it here with another color for being able watching it easily. Okay, we have also information that comes from the maps. So this information, I'm going to make a zoom here. This information is not the same from the dots of different colors, the small dots, and the information that comes from previous maps. That's the information I told you that we can collect for the whole north of Spain and maybe for the whole country and the whole Europe. Just taking information from previous maps. That maps can be better in terms of suitability, in terms of quality, in terms of accuracy, or whatever, or in terms of the similarity with the classification typology that we define. Or we can be worse. They can be better, they can be worse. We can keep the information. We can keep the location of different points that can be structured using different approaches. We have patches, so we can first generate random points, or we can use different criteria, as I will try to explain you now, using the predicted variables that will be used afterwards in the modeling. So in this case, just for making it simpler, well, that doesn't matter. We have here the green points are information that comes from the maps, from previous maps, okay? And the other points come from the field. So the information that comes from the fields, is not going to be subject in the beginning to uncertainty in terms of, we believe that if a botanist, if an expert go to the field and locate a point, we believe that that information is accurate in terms of spatial location, in terms of content. But when some information comes from the map, we can do our best to locate that point using different GIS tools in the correct position, but we, in the most of the cases, don't know what happens within the patch. That's what I explained you. I showed you before in that slide on which you can see a vector, a landscape patch that is located in an area that is supposed to be covered by forest, but in a shadow slope, we see that we have no forest there. But when the photo interpreter draw that line, he or she considered that that was included within the forest land cover, and we accumulate an error in the landscape patch that we will keep that error when creating points for representing that patch, okay? So what can we do here? So we can use the information from predictor variables. So we have different predictor variables. We have information about from NDVI, for example. We have information from slope. We have information about the different variables, precipitation, temperature, and we have information, I have not here, it was an error, sorry, I will put it now. We have information about the about LiDAR. So the issue, I didn't include LiDAR here because we have no LiDAR in all the countries and open available information from LiDAR in all the countries in Europe, in all the case studies of ALICE, but we have it at least in Spain for the case study. So if we use the information from LiDAR, we can, I'm going to look for the LiDAR information. Spain, environmental predictors, LiDAR. So I can do this example with all the information that we want to use, but let's go here in detail to an area on which we have information about LiDAR. Here in the legend, you can see that we have colors from black to white. That means that when the pixel is whiter, it means that we have a higher altitude of vegetation. If we go to the, I'm going to uncheck the NDVI. If we go to the orthophoto, we can see that in the areas on which we have forest, we have an information of LiDAR telling that the vegetation is not zero height. It's has a value of height over the ground. Okay, so in the areas on which the trees are higher, LiDAR informs us that the height of vegetation is higher. With NDVI, we can also do something because we have a value of NDVI higher when we have greener vegetation, when we have something that is not ground data. But as you can see here, if we use only NDVI, if we use only the information from multispectral imagery, we cannot be sure where we have forest or where we have other thing that is vegetation, but not with tree stands. Okay, so as far as we can go with the predictor variables, better will be for assessing if our information of our training information is more or less accurate. If we have time, I would go in detail into the typologies of the different of the training data that we have here, but I will tell you just to imagine that we use now simple GIS tools for identify which of our training data is forest, which of our training data is shrubland, grassland, of course, labeled with the different units typologies. So if we have information of which units typology is our training data, sorry, I want to here the units, okay. This point is forest because we have a units typology is talking about a Quercus forest. So at least in the beginning, just to make a simple example of this, if we open our LiDAR information, we should have here a vegetation height that was over that has a value. I select here LiDAR. This value need to be 4 meters, 5 meters, 10 meters, 2 meters. So it's not a very mature forest type that we can check in the orthophoto. It's a forest type of around 3, 4 to 6, 7 meters that will allow us making an extraction of information that can be added to our information from the training sites. Using, if we go to our GIS, wherever you use ArcGIS, QGIS, or R, you can do a simple analysis, spatial. Here using in ArcGIS, using spatial analyst, you can make an extraction of each of many raster layers. You can include as raster layers are predictors as much predictor layers as you want. Here you have in the first you have access to the material of the hands-on exercises of the workshop, and here you have some variables. In the first hands-on, you have a guide on which would you have a presentation, and you have a data folder on which you have the units I am showing you with the different codes. You have the variables that you can use in your GIS for including in this kind of analysis that will add the different information of the variables will be added to each point of the training data that you have that can be afterwards used for filtering if the points that we collected from previous maps are true or are not true, truly related to our units typology that define each point in the base of expert criteria. We can never have forest or a shrubland units type if our NDVI is value 0 or value 0.1. We should not keep that point because the uncertainty will be quite high. If we have LiDAR, it's very useful for identifying areas that have a tree stand typology or not. So with this kind of information that is collected in the database of the points, we can just take that Borja, as Borja explained, we can make, sorry, I'm going to close this. We can, sorry, I'm going to, yeah. we can use this information for, as Borja told, and the word that he used was filtering our training data, but independently of the origin of the information, it's much better if we have in situ data. But if we have not in situ data, we can use map data for selecting random points, or with more a locally tailored design strategy for selecting that point. But finally, we can filter that points with the training data for being as sure as we can that the point is really talking about the units typology that we define for each of the points. Once we filter and clear this training database, we are already I'm going to stop the presentation of the GIS thing and going to, just for being sure that you are watching the presentation. Once we do that, we have our training data. Okay, we have been talking about the classification system. That classification system is transferred using different sources of information with higher reliability, with lower reliability, to the occurrence data for training and for validation. We can use our predictor layers for filtering that training data and being sure, even though in reality, the botanists are 100% sure of what they are talking about. We need to be also sure that that information matches with our GIS environment. So it's important to be reliable with in situ data, but it's important to be reliable in terms of our GIS environments. So we are talking now about predictor layers. So predictor layers, as far as you know, is the information that we need to collect for extrapolating our training data, but you have also seen that it needs to be used previously, but for filtering that information that we collect from somewhere, okay? So talking about predictor layers is a big world. We can spend 1 month talking about in a course only about predictor layers, because we can talk about everything. So that just for making it operational and making it easy, we split the variables into groups. On the one hand, we have the environmental limiting factors. I mean, we have information about the distribution of topography and surrogates for climate, precipitation, temperatures, radiation, and everything that can allow us explain the distribution of biodiversity, of vegetation, in the shape of habitat units, habitat types in this case, and soil properties. Some of the information is easily available. We can go to the web, and we can just download the information about topography or whatever. Or we can we have to prepare that information, but it's everything related to environmental limiting factors for defining something that is more or less potential in terms of where the different vegetation typologies can occur in space. But also we have the remote sensing with the multispectral imagery, multispectral because of the availability. We will talk about hyperspectral afterwards a little bit. We have information about LiDAR, about radar, and we have, of course, different, also information about the drones, flights, and so on. And that information can be used for developing indicators of the distribution of the vegetation patterns that we have identified previously in terms of accurate as possible training data. So as I explained,
just hold on. I have a question for you from the chat live. I think it would be good to make a short break as well to make this winter school more interactive. So Dimas Pereira Ubaya asking a question about, okay, if we want to make a change analysis between a moment back in time and today, can we use thematic map instead of field data to train and validate?
Yes, if I understood the question, yes, if you want to, well, that's something that we will be answered at the end of the session about habitat mapping, actually. But we have to use our imagination and our capabilities as technicians, GIS, and scientists for acknowledging which information do we have and which objectives do we have. For answering your question, if you want to track the dynamics of vegetation in the shape of habitat types, now I mean that we can go to the field and see what is going on. We can use our expert criteria for doing a sampling or for filtering the information that we have from coetaneous habitat maps. That's okay. We can go to the field and we can work and spare our time or money to do this kind of collection of training data. But if we are talking about the distribution of that vegetation patterns in the shape of units, habitat types, 20 or 30 or 40 years ago, we have no information to do that. We can use, the best that we can do is to use our old aerial photographs for making some kind of photo interpretation, or we can use all past multispectral images, basically 40 years, 30 years ago Landsat imagery with different sensors in time and so on for making classifications. But can we map units habitat types at level 4 40 years ago? I would say not. It's quite, I mean, I don't want to say not. It's complex. I mean, you have different paths for making your assessments. That one of that options is the one that we use here in ALICE, is couple landscape dynamics that can be more accurately assessed. Landscape in the terms of, as Thomas explained, talking about the structure of structural shapes of vegetation at the landscape level, forests, shrublands, different crops and so on, and then try to link the dynamics of landscape with the current vegetation patterns with the higher level of detail that we were able to map to track how the landscape changes evolve and try to link that evolution to the different biodiversity patterns. I don't know if do you think, Thomas, that that's more or less the question?
Yeah, I think it answers the question, because it is a tricky situation that trying to make some habitat maps in the past without any in-situ data sets. So
yep.
I think you answered the question, so you can go on.
Oh, I want to mention also some the magics of the data processing that is artificial, that relates to the artificial intelligence algorithms and so on. That I don't know, with the time series of information, artificial intelligence algorithms, and putting in common, I don't know what now, that is something that is being developed nowadays. Maybe we can do much more in the past that we can imagine now. But the important thing is that we need to have imagination, but fed with technical criteria. And we have to acknowledge that we have some data, and we have to handle with that. Okay. So just going a little bit more in detail in the predictor in layers, as I explained you, there are some available information that we can just download. For example, information about topography that is easily available. We can download the tiles and mosaic and have large territories covered by detailed information. We have, of course, the Copernicus EU digital vision model with very high resolution at the European level, or we have the SRTM or other approaches at the world level. But if maybe we need more accurate data, in Spain we have 5:1 already 1 meter digital vision model derived from LiDAR, and we can download and develop surrogates as a slope, also radiation, and so on. That's easy. Download and we have it. Other times, talking about climate is a very big world. The information about climate with the reanalysis and Eurocortex approaches, and of course the Copernicus. But I'm going to just show you one tips, some pictures about what we can do. Sometimes we have available information, and I have used during all the works I have done in my life, the climatic map of Ninjarola from k.LAB. That is a very interesting map. It's at 200 meters. That maybe is quite rough resolution that need to be reinterpolated using different geostatistical techniques for smoothing the information at the pixel level that we have from remote sensing and other databases, and avoiding the crisp analysis with bigger pixels. Or we can use really available worldwide data sets as WorldClim or CHELSA analysis, from which we can download information from current climate scenarios, future scenarios to work with climate change and so on. And of course, as I explained in the beginning, we have to take a look to the Copernicus world that is amazing, the good and amount of information that we have now at hand for the European domain. And finally, talking about the abiotic predictors, we have another information that is not really available, but is necessary to have at hand when we talk about the distribution of vegetation with important variables as, for example, the pH, like texture, the percentage of sand of the topsoil, the different texture, the composition in terms of the structure of the topsoil, but other information. So this information cannot be downloaded or can be downloaded directly at the world level with different approaches like soil grids or the soil map of Wageningen University that we used. But when you analyze the information at the local level, at the patch level, the reliability and the capability of that information at the local scale, local to regional scale, is limited. So we decided in some of the projects, as we did in the Spanish case study for Alice, we decided to create our own soil properties maps, going to the field, taking information in the field, going to the lab, analyzing the information, and running digital soil mapping analysis for creating information, as I showed you previously, about the texture, about the pH, and developing different approaches for soil organic matter. That was not so easy. That we ended up with a mechanistic modeling approach that we published a couple of months ago about the distribution of soil organic matter in the topsoil. That was very useful for mapping the distribution of vegetation. So with this big amount of information, we arrive here the information from remote sensing. We have different sources, different satellite imagery that we can download and prepare and put in common with our abiotic information for running analysis, ranging from Landsat information that we can download, Sentinel information that we can order and download different approaches, as Anna will explain you in a while. And of course, we can do this for, again, from regional areas, or as we did in Turkey, for an area that was almost half of the Iberian Peninsula, following more operational approaches that go in and click and download. That information that is downloaded is not as simple as download. It's information that need to be prepared. We have to identify clouds, shadows. We have to correct the information for creating maximum composite products that have no data information and reliable information for the whole area that we want to map and analyze. Derive spectral indicator, its spectral indices as NDVI and many other that we can derive from this image. And of course, we can play with the different resolution of the images that are available. We can work with Landsat, but we can jump into, for example, Sentinel that improves the spatial, spectral, and temporal accuracy of Landsat repository. But the good thing of Landsat is that we have information from 40 years ago, as our colleague asked in the YouTube chat. So with all that information, arrive new sources of remote sensing information as LiDAR and radar that informs us not only about the distribution of the different reflectance values in space, but also in the third dimension of altitude, how vegetation changes. This information is not available for all the Alice case studies, but you have an example in the Spanish case study on which we have this kind of information. Of course, many of these sources have temporal resolution, so we can play with information of phenology. We have information from spring, from summer, from autumn to get more reliable conclusions. And everything is related to the spectral capability, as Anna will explain, of the remote sensing imagery, and in this case of the multispectral imagery of differentiation between what we can see with your eyes in aerial photo and what the satellite, the spectral images, and remote sensing in general can see beyond our eyes. And this information can be extrapolated to the whole study area, giving different responses in the base of the different land covers, in this case, in the different units, habitat types that we have in our geographical space. And now I will kill my presentation to allow Anna to talk a little bit more, some minutes, about how getting this remote sensing data download and processing. Anna, are you there? Okay, we cannot hear you, Anna.
Listen to me now?
Okay, now Anna is perfect. Thank you very much.
Okay, good. Well, I'm going to start my presentation about the integration of remote sensing data into these process of habitat mapping. And well, basically, I mean, the objective of this particular hands-on is basically to understand what are the data products that are necessary for this habitat mapping. Then to have a better sense of the practices or the rigorosity of the practices, the processing of the images in order to get the best available data, and then, well, to have a little insight of how the ESA SNAP toolbox works. So basically, what we aim with this hands-on is for you to gain some knowledge about these products and the remote, I mean, the processing of the remote sensing imagery. Well, I'm not going to, I'm really going to go fast in this, because I guess that everybody has more or less, after all these presentations, a good sense of why do we use satellites for this type of mapping. But basically, as just to mention very quickly, it's basically because they provide regular and consistent observation of over large areas, which otherwise, well, is not. I mean, this allows us to monitor, actually, that otherwise it would be a lot more costly. These imagery, it has they are consistent, both in the way they are acquired, because they are sensors that they are achieving, acquiring the information repeatedly in the same way. So they provide us as well, like a well-structured time series, so they can allow us to go back in time and to have, well, to, as José Manuel mentioned, to have a better sense of the phenology, and that's an important tool for the habitat mapping. Then, well, they provide us a large number of data products, yeah, and most of them, they are for free. I mean, and they are for sure complement. I mean, they are complementary to the in situ sampling. So there are several types of optical satellites or optical sensors in different satellites, but this is a list of the ones that right now they're running, and they have free access, and we're going to focus basically on Landsat and the Sentinel-2. The first thing that you should be aware of is that there are different levels of data. So it's very important to have this clear, because in order to know what you are selecting for your modeling. So the first one is the level 0, which is the raw instrument data, and then is the data the way it comes directly to the satellite. Then there's the level 1, which provides geolocated and calibrated data, but at the level of the sensor. Then there is the level 2, which are products derived from the previous one, the previous level, and these are both geophysical products and atmospheric corrected products as well. So they provide us the spectral signature at the surface level. Then we have the level 3, which are gridded and quality control data. and then the level 4 that they're basically model outputs. So what we get actually from our modeling would be some sort of a level 4. Okay. Well, this is a more detailed explanation of this type of data, but for you to know, it's important. You know that the less the level, the greater the skills that are needed. So basically, for a person that is, it doesn't have a wide knowledge of remote sensing, a level 2, starting with a level 2, that would be fine. I mean, it's easy and it's feasible for everybody. So one of the things that I'm going to focus on is basically the atmosphere correction for the habitat mapping. Why? Because this is a key issue in order to retrieve these at-surface reflectance. That is the one that we're going to use for the habitat mapping. So basically, satellite sensors, what they measure is top of the atmospheric gradiences. So it's the signal that they receive directly at the level of the sensor, and it's a combination, I mean, of both the surface signal, but also mixed with the atmospheric conditions. And so if the atmosphere varies, your signal is going to vary independently of what's actually happening at the surface. That is the information that we want in order to retrieve our habitat mapping results. So basically, and just as an example, I would like to show you how this signal varies with the altitude. So how the atmosphere is affecting the signal that we are retrieving. So as you can see, from the surface, that is the bottom, a black line from the surface up to the top of the atmosphere. And our signal is quite different and is quite perturbed. Okay. So what's the goal? Well, basically to retrieve the at-surface reflectance spectrum. And for doing that, there are different approaches, but the most complete are the ones that they use radiative transfer modeling, that they consider the atmospheric conditions, the clouds, the aerosol information at the time that the image is acquired. And there are different as well models in order to perform these habitat corrections. So the most popular are the 6S, iCore, ArcLight, Flash, you name it. I mean, this is an example. Pardon me. And this one is focused on the target is water, but and I know that we're dealing with vegetation, but it's just basically for you to see how do we parameterize and how we retrieve what's the input that the atmosphere has over our signal. So, for example, if we do an RGB, so like if we want to open an image and we open top of the atmosphere image, what we're going to see is that it's bluish. So our image is greatly affected by all the aerosols present in the blue and the water molecules and so on. And it is once that we have performed the atmospheric correction that we obtain the surface reflectance, so we can truly appreciate the real spectral signal. So in terms of the Landsat data, well, there are different archives to access it. There's well, Landsat is part of the USGS or the US Geological Service, and so they have different types of repositories, but the most common one is the Earth Explorer, and is the one that we're going to focus on. In order to access the data, the only thing that you have to do is to set up a free account and log in, and it's very simple, very straightforward. There's not much of it's not complicated at all. Once that we're in, later on I'm going to go through the web, but I'm just going to show you a little bit, and we'll see later on how it's done. So the only thing that we have to do is either to select the area that we are interested on, or if we know the actual scene, satellite scene, we can put it and then select the date and the cloud cover and so on, and then we have a bunch of data sets that we can use. And actually, the Earth Explorer has not only Landsat data, but also Sentinel-2. But we're focusing on the Landsat one. So we select the data, and you will see that there are two different things. One of them is, as I was mentioning, at level 1. That is this top of the atmospheric radiance. And then we have the level 2 that is under demand, and it's atmospherically corrected. So once that we have selected the missions that we're interested in, we can go through, we can add some additional criteria in order to narrow down our selection. And then it's just a matter of, clicking over the results, and you will see that a bunch of images appear. And then in order to download it, there are also a bunch of possibilities. But the one that we need is the what is called Landsat Collection 2 or 1, it doesn't matter, level 1 or, well, in this case is the level 1, but we can be interested directly on the level 2. And it's the product bundle. So it's basically the overall information of at 30 meters, and all the spectral information and thermal and so on. So just to, just to resume, a Landsat 1 can be a level 1 of Landsat can be directly downloaded from the data archive, like Earth Explorer, And then these files can be later transformed into a surface reflectance, as I mentioned. But if we don't feel very comfortable using that option, we can go directly to Landsat 2 data and make a request, and in less than 2 days, you will have all your images corrected. My suggestion is that if you're going to use, if you're interested in using different sensors like Sentinel, Sentinel-2 and Landsat, which are more or less equivalent, Landsat 8 and Sentinel-2, I wouldn't use level 2, direct level 2, because the methodology for this processing is not compatible with the Sentinel-2. Right, so in that case, you will have to download level 1 files and do the atmospheric correction, which has to be the same as the one performed for the Sentinel-2. These of Sentinel-2 as well. There are different ways to access the data, but the official one is the Copernicus Open Access Hub. And yeah, for that, you have to also set up a free account and log in. It's very straightforward. Then draw the area of interest with that button, and select the data that you are interested in, because this Copernicus Open Access Hub thing is that it has Sentinel-1, 2, and 3 data. So yeah, it's you have to select the adequate one. The first thing that you will find is that you have to select the what is the period that you're interested in, for example. And it might be either the sensing period, so is the time at which the satellite passes over the area of interest, or the ingestion period, and is like the post-processing period. Normally, the most most common selection is with the sensing period. Oh yeah, and you will find as well descending or ascending, and it's the orbit. Basically, this is related to the time at which it passes. So it's daylight, or nighttime. So the descending is associated to daytime. Then you have to select the mission, Sentinel-2, and then you'll find that there are different types. In here, you will find that there are the level 1 and level 2. And you can, the level 2 is official. It's an official product, as a product. So you can go directly as in the case of Landsat. But again, you can decide to perform your own atmospheric correction. Regarding the satellite platform, is that Sentinel-2 has there are two twin platforms. There's the Sentinel-2A and Sentinel-2B. So, they're extremely similar. They're twins, and if you want to enhance your possibilities of having more data, I wouldn't put absolutely anything in here. I will just do my selection with the product type, and that will be it. So once that you select once that the area of interest is selected, and we have decided that we will go for, well, in this case, I didn't specify it if it was level 1 or level 2. We obtain all the results. So for downloaded is very, it's very simple. You have that button, and that will be all. There's something that you should know, and is that these products are very, they require a lot of hard disks because they are quite big. So yeah, to sum up, Sentinel-2, level 1B data, you can download it directly from the archive, or you can, and then later on perform the atmospheric correction, or you can go directly to level 2 data, which is fine, and it's an ISA product. So in order to visualize and process the data, ISA provided a toolbox that is specific for Sentinels, and it's the SNAP toolbox. You can download it directly from this web page. And then, well, the first thing that you will have to do is just launch your software, and you will see that there are different, depending on the version, the viewer is slightly different. So, for example, in this presentation, what you're going to see is the Mac version. But for example, now that we're going to go through the web page, or the software that is installed in this other computer, which is a Windows, is slightly different. It doesn't matter. I mean, so what we will do is just do the data opening and visualization, the atmospheric correction, which we are not exactly going. I'm just going to show you very briefly how it's done, but we are not going to perform it because it takes quite a bit of time, and it's highly demanding. And yeah, you can do it with your computers, and then we'll see the spectral indices. So, for example, yeah, this is just a snapshot of an image. It was open of the area as a Sentinel-2 image. One thing is that the snap also allows you to process Landsat data and different other sensors. And yeah, and here this is level 1. Well, the spectrum view provides us, well, we can see that it's not corrected because, well, it has, the blue is very high, it's quite higher than the what it's supposed to be. But well, and we'll see it later on. And then, yeah, regarding the atmospheric correction, SNAP allows you to perform different type of corrections. The standard one is the send to core, that it would be a replica of the I will say it, of the official product. The reason why this model is installed in the software basically is because, for example, in the case of the Sentinel-2 data that is installed or archived in Earth Explorer, is only level 1 data. So if you want to perform it, exactly the same way, or to have exactly the same product, official product, as the one that is provided by ESA, you can use this Center Core. The problem with this atmospheric correction is that in hilly or mountainous regions, the performance is not great. I mean, it's okay, but it's improvable. Then there are other options like iCore, that is a module developed by a company, Vitu. And the interesting part of this module is that it allows us to perform the correction to perform the correction both for water and vegetation. And then there's the acolyte that is also very complete, and it works perfectly fine for both vegetation and water. And then there are the spectral indices that, well, if you click on the optical part, there's the thematic land processing, vegetation radiometric indices, and there's a bunch of indices that they can be retrieved very easily. So this is an example of the NDVI. Well, I'll stop this, and I'm just going to show you that very, very briefly. I mean, this is the Earth Explorer that I mentioned before. It's very intuitive and it works fine. This is, for example, the case of the Copernicus Open Access Hub. And well, these are the atmospheric corrections things. So, for example, this is the SNAP. So I've been told that we're running a bit out of time, so I'm going to go very quickly. In order to open it, it's just this. Click on this, and it will be loaded. It's exactly what we have in here. Then, in order to visualize this data, there's right button, and then the RGB image window. And if you go through it, you can see, well, this is the level. Yeah, this is providing us the atmospheric signals. The spectrum signatures, atmospherically corrected and not. Okay. Apparently, you're not seeing this. I don't know what's happening. Are you okay? Oh, yeah. So you're not seeing this. So everything. So well, anyway, if you have any questions, I'll be happy to answer them. Thank you.
Okay, thank you, Anna. So if you can stop sharing the screen.
Yeah, I'm trying. Like, hold on. Just trying. I don't know why this is not.
So Mariana, if you can stop sharing the screen of Anna.
Yeah, I'm trying. Hold on.
Mariana, maybe you are there. So well, just for linking, we would like doing an in live exercise, but just for clicking and ordering the selections and so on. I think it's more efficient to see what Anna explained us in the presentation that you have available in the material for for following the same steps. So the issue is that we wanted to demonstrate that the remote sensing is not just clicking and downloading the images. We have to take into account the corrections and the post-processing, because of the ways that information of predictors that we use for filtering our training data, as I explained you before quickly in the GIS. I only wanted to show you that once we have our points, independently of the origin, we can check and validate and filter that training information before running analysis. And of course, when extrapolating using our predictor information, that information needs to be accurate as the training data. Otherwise, our information is not correct one, is not really something that reflects reality, and our predictions will be not reliable neither. So finally, once we have our classification system, occurrence data filtered from the predictor layers, we have the predictor layers from remote sensing, environmental limiting factors, we jump into the ecological modeling part. It's the very interesting one here. I mean, everything is interesting, but the modeling is the more visual one. We put the occurrence data and predictors together, following different approaches. I would like having 2 hours more for explaining you. I would like starting with the graphical user interface of Maxent. Just downloading the program you have in the material. You can open the graphical user interface. I gave you as well a really detailed step on document for running analysis using the graphical user interface. And then, of course, we can run more efficient analysis using R, script, or Python languages. And of course, going into deep learning with the different approaches and softwares that allow this kind of analysis. So we just directly go into the example of our scripting with Biomod 2. That Isaac Pozo is one of colleagues of that we work together in the National Museum of Natural Sciences. Will show you how to couple these training data and predictor layers for making our predictions. Stop. And leave Isaac to tell in a minute this one example on this. So your turn, Isaac.
Okay, hello everybody. So can you hear me now?
Yeah, perfect.
Okay, so I will share my screen and let's start. So it's something that I want to tell is that I'm going to try to show you how to program live. This is really very difficult to do it in YouTube. I'm going to go as slow as I can, but this session will be recorded, and I have tried to save all the steps. But just in case if you get lost, just let me know. I will try to go as slow as possible. Before passing to the presentation, if anybody of you wants to follow me live, there's one step that you have to do it. That is basically install the package Biomod. This is our library that needs to be installed. It will load series of packages and it can take like 1 or 2 minutes. If you never have worked with spatial data before in R, I just recommend you to run this line, that it will load all the different packages that you might need. Some of them you maybe should have it. And while that is happening, I will go to the PowerPoint presentation and show you more or less tell you what I'm going to show you. But let me know if you get lost. So basically, Jose asked me to show you how to do spatial modeling. So basically, with the basics of bioclimatic modeling is just to compare what is called the geographical space and the environmental space, and to project how we have a set of species. Where is the niche modeling? So we are modeling the potential space of a species, not the real occurrence. So we say, according to our variables, to these environmental variables, this species or this habitat should be here. Otherwise, is that the humans has decided not to do it. And for example, I can say here is a potential of a beech forest, but otherwise it's a city builder. So I will have to then remove these parts. But basically, we have the geographical space where I have the crosses where the species occurrence are. The gray is where the actual distribution is there. But then I will have the environmental space, that is the geographical variables that explain this, and with that I will just project to the upper box the potential zones where the species can be. Let me see if I can. Well, I cannot. I can point, but you can see in the site number 2 that the species is not there, but its potential there, and in the number 3 that the species is not there and its potential in the future, but it will have to move there. So, I mean, this of course is much more complicated, and this is going to be just to open the appetite on what can be done here, but it's just to show you. Just to make an example, I'm going to show you with the Atlantis acidophilus fagus forest. So it's the classical beech forest of high altitude mountains. So this type of forest only occurs occurs a lot in the Atlantic space, especially in France, England, and north of Spain. This is fagus forest accompanied with Quercus ilex in the small forest. So it's according to UNIS is G16.2. We're going to use the environmental space using the Copernicus data that previously has been shown. And just to show you the resolution is 10 by 10 meters, so it's quite deep. Talking about the environmental variables that we're going to use 20 environmental variables, starting with this with the weird names is the Copernicus bands that correspond more or less with what we wanted to use, but also is DM is a digital elevation model. We got East Spain, it means the orientation to the east, and DVI for different periods, being July, April, and August, because the response will be different. And with all this, we're going to model. If you enter in modeling, and down below you have the let's say the Bible of papers in this. There's a lot of modeling methods. I'm going to use Maxen here, but just to know that there's a lot of it. This is a whole science itself. Just if you want to go in deep, I will give you later reference on this. Well, we can model things, and I think this question just appeared before. The most classical study will be to model actual and future conditions and make climate change studies. But of course, you can do crop estimation, you can do parasite expansion, you can do a lot of things. So here you have two of the type example. The left one, it will be the climate change, where new climates and disappearing climates exist, and you can see how fast this is going to happen, and if the species are able to stay or have to migrate, or we have to implement measures as translocation of species. On the right side, you have an example with the giant Asian hornet, that, if you know, more or less is displacing the honeybees especially in America, but it's basically it enters in the colonies and kill the queen, and it decreases population. So we can see the expansion when it arrives to the east coast of the States. You have there below the paper that make it, and see how it goes. So, okay, so as you see, we have a lot of mixture things. We have a lot of initial condition, a lot of models, a lot of model parameterization, and a lot of boundary condition. And on a paper of 2007, Miguel Araujo and Manu just proposed this ensemble forecasting that is saying, okay, we're going to plus all models and get where most of the models say the truth. How we do this, there's a lot of ways of doing it. There's a lot of packages that do that. That's a lot of possibilities. For this presentation, we have chosen Biomod 2 because it's one of the most used. But there's many other. There's the paper there where we're explaining a lot of it. But just to show you a little bit, we feed the model with species distribution and environmental data. We just give single models. We just parameterize every model, and then we go to the right part. And so we do all the predictive space. We train a model and do ensemble forecasting and generate a new model. So let's go on to the hands-on. If you enter on the materials of this exercise, you have a series of folders there. The one that I want to show is the steps one. If you get lost, I have saved the R workspace in 3 parts of the script. So if you get lost, you can go directly to that part. On the script folder, obviously, is the script that I'm going to use. And on the modeling folder is where the simulation is going to run. You will have it empty now, but in the end, it's going to be filled with this. So with that, let me show you the presentation, the R. So I'm going to show R Studio. Can you confirm that this is being seen? Just in case.
Yes, it is. It's perfect.
Okay, so again, this is not, YouTube is not the first, is not the best way of showing this, but let's go. So first, if you don't have this installed, please run either one of these two. Then what we have to do is basically load the libraries needed. Not to go very in detail, but I'm going to load library by mode, a series of raster and spatial management libraries, and something like that. This is something that I do normally just to have a clean explanation, a clean version. I just clean all variables, so I don't have nothing on the right side on the variables. Then I will set the working directory. So if you have ever worked with that, I'm going to do it manually here and choose this directory, but you can do it by coding. So I will just say that I'm working here in Ali's seminar. So if I get my working directory my computer is behind me. Okay, so if I get my working directory, just to know it, we're working there. Okay, so the process will be split into pre-processing, model processing, and studying the model. So in pre-processing, I basically have to prepare the model. So I have a save file that I can read. Oh, okay, so we start early. Hey, that was my fault. I already entered in the folder, so I can. Okay. Well, let me go to another session of R. Sorry for this is the live things where I have everything loaded. So if I just load the script, so this is the same, but basically is in my with my path. So if I just run this part and I load it, and I don't know how fast it will go, but basically I'm loading a save file with the species distribution, and it's going to be a little bit slow, so I will skip a lot of these things. But basically I'm loading a save file. Next thing that I have to do is just to build a table with 4 columns: the species, X, Y, data, and response. And with that, I'm basically playing with data, deleting columns and adding columns, and so on and so forth. And finally, when I have it, I will show you. Wow, it's taking a lot. Okay, so later on, I'm going to stop it, right? If you don't mind, just to show you as much code as I can in live. Cool. Okay. Yes, interrupt the session. Okay, so then what I have to do is load the variables into our format, into a stack format. Again, here is how to do it in code. Basically, you just list all files with the final extension, and then I put it on a pile on a stack, and then I plot all of them. All this is done. So first thing, if you get lost until here, sorry, I have it down here. So here you have the loading, the step that I made it. Next thing, and I'm sorry trying to go as slow as possible. So I need to format my biomode, and I have to tell a sort of parameters, just like where are the present species, where are the X and Y coordinates, where are the characters, so on and so forth. I have to set up the biomode characteristics. Okay, I have it finally back the program with me, and I have to configure the model parameters. Just to show you what are the type of parameters. Let me see here if I can plot this one only. So my parameters will be, okay, it's going slow again. Sorry. So this is the type of parameters that I can put. I just can modify the type of parameters, the type of models that I'm running, the type of iteration. Okay, it frees. This is great to be live. To show, let me go to the different RStudio just to show you the script, and I will go back there. What I'm showing you is, sorry again, sorry, I'm going back here. So you can modify all the parameters that you want. One important thing, you're going to have a problem for sure. I don't know why this never works. Maxen is making weird things with R. So if you have an error, you will need to download from here the maxen.jar and put in the working directory. So once that is done, what you have to do is run the maxen model. I can tell here, I try to comment the script as much as possible. So you can declare here as many models that you want. In this case, I'm going to just run maxen, tell the option files, tell the number of runs that you do it, split, and I've tried to send you all the information that I can. And then finally, well, here you have another step. So in case you want to load it, and then I'm going to run the ensembles. So basically, again, is commented as much as possible. So I'll tell what I'm going to do, what is the metrics that I'm going to use for examples. Again, there's a lot of bibliography around that. I'm going to use true skill statistics. But again, there's a lot of things around here. Later on, I will project my model to the present, to the territory. If I have future data modeling, I will be able to project to the future. And then finally, I can study the results. So let me see if I can go back. Otherwise, I have it in R. I have it ready in R if it's in ArcGIS if it's a problem.
Isaac, so, there is a question for you about
yep.
Selena. She's asking that if it is possible to model multiple species at the same time.
Yes, of course. This is normally what we do. Just working with one species is just more for demonstration, but normally we just run hundreds of species. Hundreds, yeah. But we run 20, 30 species. But as much species and as much model, you need a more powerful computer. Just to benchmarking, I have a pretty decent computer with 32 gigs of RAM and a pretty good processor, and it's taking like half an hour just to do the full process. If you go for real with everything, we can talk about a day of processing in a powerful workstation. But yeah, this is something normal. So, I mean, the script is more or less trying to tell you everything, but I'm more interested in showing you the results. So if I go back to the presentation, sorry, I'll go back here. So once I do the model, I can have a lot of stats, and I'll show you the stats if I can. Sorry, not this one. Here. Okay, so once I run the model, I have 100 of stats, and I don't want you to lose too much. But basically, I can see the sensitivity and specificity of every model. So if I cut on the 90% of sensitivity, I can have the model. Just to go faster, and sorry, I can see the variable contribution, and I can find that the June June NDVI is the most contributing. The slope is also contributing, and so on and so forth. We can see all the variable response curves. We can see the map results. So if I run all models, I will have this. Of course, this is all the possibilities from 0 to 1 according to your TSS. But if I do ensemble a cut by 90%, I will get this. If I run more models, I will run them with 5 models. Oops, sorry. I will have this on the right side. It seems really similar, but it has small differences. And of course, this is just one touch. If you want to go to enter in this really in detail, I just recommend just these 2 books. The one on the left is the popes of the disciplines, the more mathematical, the more practical. The one on the right is more hands-on with application with R. Finally, all these things can be put it in R, and I can show in ArcGIS, and I can show you the model. I can show you the 5 models, what is, and I can show you all together. And it's not loading. Great. Okay. And just to see the small differences, if I just zoom somewhere. So green is where both models just agree. Red is where my maximum model works, and blue is where the 5 models. So you can see the pattern is correct, but the difference are between 1 and 2. And I think is that for the moment. I mean, I know this is just too quick. I know that YouTube is not the best place for explaining R, but it's just, as I told you, just a little bit of open the appetite for that. Thank you very much, and if I will be here for any question.
Thank you very much, Isaac. We spent a lot of afternoons and days and months and years discussing about these things, how it works or not in a museum and beyond. And it's an amazing job. It's an amazing work that you can do working with these modeling tools that allow us, as I explained, to put in common our occurrence data and with our predictors to get our spatial predictions for getting finally maps. So when we started talking about the botanist going to the field, we get maps. So after this whole development of occurrence data, training, classifications, predictors, and modeling approaches, we get at the end maps, as Isaac explained. And that's a very important part that we have to understand, to conceptualize when talking about the habitat mapping. So when modeling, we can only model using environmental predictors, abiotic limiting factors. So we will get information about the potential distribution. Let's call potential distribution. We are talking about communities, not the species, but the concept Isaac explained is the same, that when talking with ecological niche, that geographical distributions, we are talking about habitat distribution modeling instead of species distribution modeling, but it's similar. When remote sensing arrives to the equation, we make some kind of detailed analysis on in which locations, as Isaac explained, as these habitats occur. And when we put in common different the outputs for different habitats, we reduce the omission errors, and we get something related to the real distribution of the vegetation types in a space. Using the individual predictions. That's very well explained in a paper that we had that we published a couple of years ago, talking about this concept of the area of occupancy of habitat types with remote sensing. As I explained, it's something similar to the BAM diagrams of the species distribution modeling community manages, and maybe some of you knows well, on which we reduce the potential distribution towards realized distributions of the species, and in this case of the habitats. So when we include remote sensing in this community modeling approach, we go through the potential distribution, as you can see in the upper right part of this image, to realize distributions of the different habitat types. That's what we call potential, local, and realized area of occupancy. So I am not going to go into detail because we have no time, but you can go read the paper and understand this a little bit better. Of course, the area occupied decreases as soon as we introduce better predictors and we put in common the individual prediction of different habitat types. So in terms of maps, that is the easiest way to understand this. What do we get? So what we get is the information, continuous information for the whole study area from which we collected training data, from which we collected predictor layers, the continuous distribution, the continuous probabilistic distribution of each of the habitat types at the units level, I remember, that we collected with our training data. If we put a threshold on that continuous probability, we can get finally something that is quite similar to the maps that we create with photo interpretation. I don't want to say it's better, it's worse. It's another way of producing the maps that will give us a similar information in a space that we can photo interpret. Then we will validate all this to see how good has been our work. So as Isaac explained, when we model only one habitat, we can get what we call the local area of occupancy, the local area of occupancy. But when we have multiple predictions, we can create algorithms that combines the dominance of each habitat type, the uncertainty of the individual predictions, taking into account complex statistical issues like the prevalence of the training data and so on. We can spend 1 week talking about this, but just believe on that we can handle, we can manage all this information for getting finally continuous maps for the whole territory on which we optimize the distribution of each habitat types in terms of the dominance of each one and the uncertainty of each individual prediction. And at the end, we have in a GIS something similar to a vegetation map on which we have landscape patches with the distribution of the dominant habitat types within them. For example, we can get a patch of forest habitat or forest distribution with the distribution of the different habitat types that are forest and are within that patch, maybe forest isolated patch within a matrix of shrublands or whatever. So at the end, the result is similar to the one that we get with typical photo interpretation analysis, but each pixel can be tracked in terms of the suitability of the habitat type that dominates and which predictor variables allow that habitat types to dominate, tracking the statistical analysis that we have done as Isaac explained very well in R or in any other environment. So at the end, we get these cool maps like we have, for example, in the project of Turkey. I show it because it's big, quite large, and we have the distribution of the different habitat types. But, and of course, we can publish papers with that, but we need to validate. We need to get independent information from the botanists, from the same ones or the others, and put on the table the information and see how our confusion matrices are good or are not good. Of course, we can put again our individual maps, our predictions of habitat distribution, we can put in common with the original maps that we use for training data or other maps that we kept for validation to see the agreement. For example, we can have the Korean land cover, we can have the forestry map of each country, and we can check whether the information that we have at the patch level in these maps agrees or not with information that we have predicted with our mapping approaches. We can use different maps, the typologies will not be the same, but as Borja explained, we will have the paths to change the typologies, and we can play with that to make a validation. So the individual predictions, the combined predictions are probability distributions, probability maps that we can convert using thresholds to maps, and we need to validate with independent information. As Gonzalo from the IHC team will explain you with the last hands-on. So everything is yours, Gonzalo, to show some tips of this GIS processing approach.
Okay, can you hear me?
Yeah.
Yeah. Okay. Okay, thank you, Jose. Hi, everybody. My name is Gonzalo, and I'm going to make a practical exercise about habitat mapping and validation for probability classification raster. In the step 1, we load the probability classification raster in the R map. Sorry. Okay, we can see that the values go from 0 for surfaces with low probability to 1 in surfaces with the high probability. In properties, we go to symbology and classify to assign two classes with a break value in 0.6. Select. If you compare with the original classification raster, you can see that the occupation surface of the habitat is being reduced. To work with values of absent and present in ArcGIS tools reclassify, we select the probability raster as input, the value file as raw class, and we assign an output of 1 for values for 0.6 to 1 and an output of 0 for the rest. Finally, we select the output raster always in TIFF format. Okay, now in step 2, we are going to apply a low pass filter to the raster obtained in the previous step. The effect is that the height and low values within each neighborhood will be averaged out, reducing the extreme values data. To do it, we use the tool filter. Then we select the absence and presence raster as input and the type of filter, in this case, tape low. And finally, we select the output raster. Okay, the result is a new raster with continuous values from 0 to 1. We repeat the previous steps for a better understanding using a new break value of 0.8. Symbology, classified, two classes, classify again, and 0.8. If we compare again with the last classification raster, you can see that the occupation is reduced again. Here. Again, to can work with values of absent and present, we use the reclassify tool. Sorry. Select the output. Okay, in step 3, we get the confusion matrix for the final classification. For you test it as the ground truth data, we will use the training points original. Okay, first, we create a new field in the point shape. We select a new name and the type of source integer. Load in the ArcMap, open attributes table. select add field. Okay, we assign value 1 to every row with value at 2.5x in unit 4 and 0 for the rest, using the select by attributes option in the attribute table. Okay, select by attribute. Unit 4. We get unique values and select everything. And now we go to the calculator and value 1. Okay, now we are going to use the extract multi-values to point tool to assign each one of the set points the value of the final classification raster. Final classification. Okay, you need to delete the save and load it again. In this case, it's not necessary. Okay, next we use the tool frequency that creates a new table containing our field values and the number of occurrence of each one. We can use the save point as input. Select the name. And select the true data and the final classification. At last, we use the pivot table tool to create a new table from the input frequencies by reducing the redundancy in records and fitting one-to-many relationship. With this table, we can check how many points of ground truth data are correctly classified in the final map. First, we select the classification, the pivot file, the through, and the value, the frequency. In the example, we get 32 correctly identified points out of 84. With this data, you can now calculate the overall accuracy and the commission and omission errors. Now it's your turn to try a new brick values to get a better classification and try with other habitats and have the final mosaic map. Thank you very much and see you soon.
Well, thank you very much, Gonzalo. And we go to the final part of the session. And I thank you very much for this presentation that together with the one from Borja, Ana, Isaac, and now Gonzalo, wanted to show you that creating the maps is not just clicking something somewhere and getting the information. You have many steps in between that sometimes, I don't want to say are boring, but are tedious steps that we have to think about, have a deep knowledge on what are we talking about. So I share my screen again with the presentation. Okay, so just to make some 5 minutes remark highlighting that sometimes, even though we do everything correct and we download the images and correct everything perfect, we have a classification procedure, good training data, our predictors perfectly organized it for running our models. Sometimes the complexity of landscapes allow us to improve our capabilities by changing the predictors, going to the field with more expert knowledge and getting more data, for reducing the uncertainty of the prediction because of the uncertainty of the capabilities of our predictors, mainly related to the capabilities of the spectral, spatial, and temporal resolution of satellite imagery. So this is an example of the colleagues from the coastal, that work in the coastal areas here at IHC Cantabria. With two classifications, with Landsat here and Sentinel here, we can see that improving the resolution of Sentinel improve the predictions in these coastal environments. This is an example that we have been working also with wetlands here in Cantabria, that we tried mapping with Landsat, we tried mapping with Sentinel only, Landsat and Sentinel, both with temporal resolution for including the vegetation phenology. And finally, we create a fusion, and we made fusion analysis with Sentinel, with very high resolution satellite from Deimos, also with LiDAR topography, getting finally more suitable, more reliable predictions. We are working now with the grasslands, also in the Cantabria region, including also the Alice case study, where we go a little bit more far away, and we have gone to the field, identified the different typologies, and we have been playing with all the capabilities of the medium resolution, Landsat, Sentinel, and MODIS, and we finally concluded that we need to go to the field and work with the hyperspectral capabilities. We have here at the IHC Cantabria an hyperspectral lab that Anna and other colleagues manage and use the different tools that we have, creating a spectral library from different vegetation types and vegetation communities with the capabilities of this lab, with the file spec 4 that have very large capabilities of assessing the reflectance at a very detailed resolution of the wavelengths. So we work with the different species, with the different communities, but also with phenology, going to the field to take the spectral signatures, the hyperspectral signatures of the different communities, going also to the lab to calibrate that observations to be sure that we have been talking about, or finally being able to identify which communities can be differentiated with other communities, and how these differentiations using approaches of spectral angle mapper can be seen, which these of kind differences can be seen with the medium resolution typical satellite images as Sentinel-2 and Landsat. With this information, we make like trade-offs between the classification procedures that we have been explaining now with the modeling approaches using in situ data and the real capabilities of the spectral resolution of the satellites and our whole predictors for predicting that thing that we want to map. So we are not going only, with supervised classifications, but we are going into the high detail of the capabilities of remote sensing and how and when should we use for creating that predictions properly. So everything is it's some kind of a feedback with the occurrence data, with the predictor variables using remote sensing for creating the community level modeling approaches for creating our maps that will be validated and each step improve the capabilities for prediction. We don't stop. I want to spend just a couple of minutes. We don't stop in mapping patterns, but we want to map processes, the dynamic of the system, and the functioning of the system, and in brief, to mapping the state of conservation of the habitat types. We have been making an effort with one colleague that is working on this, trying to understand all the guidelines that the ministry is putting on the table to doing a monitoring of the habitat types. We are studying quite deeply all the recommendations of the ministry for creating finally our final pool of indicators that can be modeled using remote sensing for the different habitat types, for grasslands and forests. We are in wetlands. We have been already done this kind of analysis, and finally using the different capabilities of the medium resolution satellite images and the very high resolution, and also the drones, LiDAR, hyperspectral radar, and so on. We create time series of satellite imagery using the capabilities of Copernicus and using our own developments in collaboration with David, one colleague from one company quite close to our work here at the IHC Cantabria. And in such a way that our real information on the ground that we have from the botanists that I told you is not only talking about, it's not only about the presence or absence of a community, but also about the conservation status of that community, can be tracked with the time series of satellite imagery, going not only to download the images, but to identify the problems of that images, clouds and shadows, that also smoothing the time series of information, or finally getting indicators that allow us to identify what happens and when some kind of changes and some kind of dynamics that allow us understanding what is happening with that patterns that we observe now, that we can track from the past, in the past, with the approaches of landscape dynamics that Thomas told us in the beginning. So just going to give you 5 minutes, I will go after hour, but 5 minutes, talking about all this information is not used only for mapping with no objective. Here in the ALICE project, we have the objective of understanding landscape dynamics for improving the functioning on landscapes towards multifunctional, towards creating or helping creating multifunctional territories in the way of ecosystem service provision and supply was better through the development of blue and green infrastructure networks. But we can just track monitoring for reporting and of course creating management guidelines to improve the landscape. So we move towards the changing landscape to something more functional. That, for example, this example is talking about vegetation dynamics. We not only want to know where a landscape changed, but also why and how that change has affected the function, the ecosystem services, and how can we improve this through the development of time series of satellite imagery informing about indicators that give us information of that dynamics. So at the end, we can understand the whole process, afterwards focusing on the changes and on the processes that we are interested. This is an example of how forest dynamics controls that one of the main topics researched within the ALICE project, how landscape dynamics and specifically forest dynamics affect the hydrology of the water basins in terms of water quality, water quantity, flooding, and many other aspects related to the river functioning. So some dynamics and some patterns drive us towards good functioning and provision of ecosystem services, while others that we can identify now in a spatial explicit way need to be restored or improve the function of that system. So in terms of management, just to simplify, we can well conserve, we have preserved that areas that work suitable in a suitable way, or we can restore other areas that are not working properly. As soon as we have the habitat maps, as soon as we have the distribution of the biodiversity patterns, and we have the information about landscape dynamics, we can know at each point if we have to work in the structure, function, in the distribution of that habitat, in the pressure that are altering that disturbing that habitats for making that restoration actions more effective. So we can disentangle, we can split that restoration actions in different indicators that will be the indicators of conservation status that we mapped previously for identifying the conservation status of each habitat type. So we know the patterns, we know the indicators that inform us about the conservation status, so we know where we have to work for improving that patterns. We can include everything in a chain process that we have well defined now, for creating also a priority index that will inform us on how and where and when we have to work on that indicators of conservation status for improve the final pattern of our biodiversity of our landscapes that will improve the functioning of themselves. So just to show you an example of how to do this instead of going to the GIS, because as Gonzalo explained, there are many steps, changing the tools, opening the tools and running the tools. This is a quick example of how to proceed. So we have everything that we explained before. We have the the distribution of the habitat types. So we know where we have the habitat types. We know how that habitat types are distributed in terms of different indicators that we want to track the guidelines of the ministry, and we will add others that are not included in that guidelines, but we or the bibliography, the experts have used previously. We are collecting a very complete data set of indicators. So we have everything distributed in space and through time. So now we define management areas. We have some landscape features, as Thomas explained, on which we focus our analysis. In this example, is the Nature 2000 terrestrial Nature 2000 areas of Cantabria. The eastern part are included in the ALICE project, but you have the whole picture, on which we can overlay the information of the distribution of our habitat types. Okay, so if we, as Gonzalo and Isaac explained, if we cut that distribution with a threshold, we can identify the areas, the local area of occupancy, the current distribution of that habitat types. If we go in detail, so we can identify the areas on which the habitat types now is distributed. We can identify the areas on which the habitat types is distributed, but in a bad conservation status because of different reasons. Structural, functional indicators will inform us on where do we have let's say the habitat well expressed and the habitat with low conservation status. And just to make it simple, we can identify for each, we can identify for each of the landscape patches, the management units, we can identify on which of them do we have our habitat well distributed, in which of them do we have the habitat in a bad conservation status. We can also identify how, for each of the habitat patches, how landscape evolved in time. Imagine, for example, that we have one area with a bad distribution of one habitat type, let's say Acidophilus beech forest, but we identify that in time, in that landscape patch, forests are expanding. So we know currently that the ecological status of that habitat type is not good in that location, but we know because of the landscape dynamics, and this may help to understand the question that was stated before. We know that the landscape dynamics are evolving towards a forestry area in the future in that location. So maybe the habitat is not well preserved now, but maybe in the future, if forests evolve with no disturbances, that habitat will improve in that location. So we can map that. We can also make landscape structure analysis and know the connectivity, as we will explain later, the fragmentation of that habitats in any of the conservation status that we want across space. We can identify pressures like fire risk if we have in that patches, the existence of alien species. We can identify things about primary production with time series, as I explained you, of NDVI or other indicators. And finally, we can use some kind of systematic conservation planning approaches or multi-criteria analysis or whatever to identify the areas that are that we can prioritize for conservation, that we can prioritize for management in the different options that we can manage the territory. Of course, we can include simulations in the future and the climate change for getting information on how this landscape will evolve and how that can affect, how that can stress our vegetation patterns to take decisions in terms of climate change and in terms of improving the functioning of our landscapes, of our biodiversity patterns into the future by having differences between now and future and include in our decisions. That's what we did in this big project in Turkey. Finally defining the Nature 2000 areas most suitable that fulfill all the criteria that I have explained you for defining really functional Nature 2000 areas. And of course, that's what we want to do, as Thomas explained in the beginning with Alice, going from satellite data to collaborative management by taking decisions in the base of all that big sort of information that we have developed. And just for finishing, if we put Alice into practice, and in the GIS again, I'm going to demonstrate because I don't want to use more time that we have scheduled, but we can go again to our training data set, to our study area. We can go to our small subset of our study area in Alice. And here we know we already have information about the landscape. We have information on how this landscape evolved in time. We have information from the past, information from now, information from the future. So the different land cover patches that we have in the territory that here in ALICE is a mixture of, as Thomas explained, of LPIS databases and some kind of topographical constraints. We have the different land cover patches. I'm going to put it here. That in such a way that we can get from each patch the dynamics of the landscape, as Gonzalo explained, we can get the distribution, the maximum probability of distribution of the different habitat types for each patch. So in such a way that we can run afterwards analysis on how that landscape dynamics is related to the biodiversity patterns. That is something that we are now currently working with the ALICE project. So we have given you information about the all case studies of ALICE. We have a detailed explanation of each step and also the script, the R scripts that somebody asked in the folders that we gave you for putting ALICE into practice by yourself, running examples. And of course, our emails, our contact is there for helping you for more discussions and for going a little bit more into how habitat maps can be linked to landscape dynamics for improving the functioning of our landscapes and finally our quality of life. And thank you very much.
Thank you, Jose. Thank you, Jose, for your very dynamic session this morning. I think that, okay, it is 5 past noon. The winter school will make a lunch break now, I think, and we will start at 1:30. So I think that maybe we can think about some questions. If people have some question for maybe 5 minutes or very short period of time in order to let people have the time to get lunch. Otherwise, you can just be connected or connect back to the live channel just a few minutes before 1:30. Jose, there is a question for you, but it is something maybe very detailed. Basically, I would say I really like the way you describe all the chain of going from satellite images to habitat mapping stuff, and all the way you are including all this suitability analysis based on different management strategies, based on different landscape units. And I think it is a very great example about what we can extract from these satellite images and all these modeling tools. And I think it will be very helpful for all these attendees. And I think it is a very good example. I think that, okay, maybe there would be some frustration because they won't have the time to follow in detail the practicals, but I'm sure all the documents you provided online would be very helpful to make them able to reproduce all this analysis. There is a detailed question about the time lag of transition between grassland and shrublands in mountains area, about the time from 2 to 5 years, but if you have any information about that, but maybe
yeah, yes. Quickly, when you, of course, we are constrained by data, but once we have a really detailed question, as for example, how the transition between grassland to shrubs evolve after a fire, or how that transition evolves with no disturbance, but just because of secondary succession, ecological succession, we can just attack to that question in a different manner. If we have to identify how shrublands appear again after fire, we should have to use a really time series of satellite imagery with high temporal resolution. That's what, for example, I did in my PhD. And we identified that 2 to 4 years after fire, shrublands become shrublands again. So that's theoretically defined as the resilience, very auto-succession communities that appear again after fire. But if we want to track how the shrubs appear colonizing the old fields and forests become forests again, we need to have more time span. We need to go with aerial photographs, for example, to the middle 1950 until now with the same data sources for having the same uncertainty in our predictions, and then compare the maps. I did as well also in my PhD. I can send you afterwards some of the papers. And we detect that we need more than 20 years for having a forest when forest was cleared before. So it depends on the question that you have to realize of the information that you have at hand, and then apply the analysis just for being current to the question.
Okay, and one maybe last short question. I was wondering that maybe your analysis, all you demonstrated, can be very sensitive to the quality of the land cover maps that is produced at the very beginning. Do you have any idea about this sensitivity in terms of outcomes of your modeling tools or not?
So sensitivity is
about if the classification of the land cover maps at the very beginning are not good enough, how could be the influence of the outcomes of your modeling, habitat modeling?
Yeah, we actually are in the ALICE context. We are making all the analysis. So we are running the habitat models within the context created by the landscape maps. So just agreeing always that we only have habitat related to forest where the land cover maps tell us we have a forest. And we are doing also the analysis without taking into account the land cover dynamics. We want to check, as you explained, we want to check whether we have commission or omission errors by comparing the landscape approach and the habitat mapping approach. Afterwards, we need to give coherence to everything. So when we run, we face this in Spain by comparing the habitat maps with the forestry map that we have in Spain, that is really is reliable, it's accurate. But sometimes we went to the field, and Borja and me spent like a couple of weeks, a couple of years ago in the field looking for the validation of these habitat maps. And sometimes we found that the forestry habitat map was quite rough, quite general, and create some patches of beech forest on which we have a lot of quercus species. And other times the map, of course, make omission errors. So, and that's something that we want to do also in ALICE. We want to just keep always the land cover map and then model only within that masks of each of forests, shrublands, and so on. But also we want to know whether the land cover approach has agreements or not in omission commission with the habitat maps. But at the end, you have to give a clear rule on how you are managing the information for being coherent. It has no sense to give opposite information, but you need to acknowledge how you are doing your work against other approaches that are in the same area.
Okay, thank you very much for your answer. So I think I will just let people get lunch. We start at 1:30 with Hugues Boussard about the tool on landscape connectivity mapping. I would like to thank all you guys from Cantabria for your effort on all your involvement in this first tutorial. And I will just wish you a good lunch and see you in a little bit more than 1 hour.
Yeah, sorry, yes, to thank again to all the people. And that was an exercise that we did for also demonstrate that we need multidisciplinarity, not only multi-scalarity and so on, but we need a lot of people with a lot of capabilities for making a real good job. And that's the philosophy of ALICE as well, not Thomas, to have experts in different fields by putting together the knowledge for getting a result that was powerful enough in all the corners that we are assessing. So thank you to Ana, Isaac, Borja, and Gonzalo for the effort for doing this, and thank you to you, Thomas.
Okay, see you later, guys.
See you. Bye-bye.
Okay, so I think we are back. We are back together for this, this afternoon of this winter school. I think that some people are not. Okay, let me just check something. Blah blah blah. Okay, so some people are getting back into the connection, and some other could have some troubles to connect so early. So, well, anyway, it's not a problem because everything is recorded. So you will be able to find all these videos on the YouTube channel from the Alice Project website. So it is not an issue if you get connected or disconnected temporarily, so you can get all the video afterwards. So I will just introduce the second tutorial this afternoon. It will be made by a colleague from France, Hugues Boussard, who has worked on, I would say, agricultural landscape changes for now a few years, and on landscape modeling as well. And he has developed a plugin for QGIS in order to make it possible to map the landscape connectivity. So this software is called k.LAB, and I will just give the floor to Hugues. So just go on.
Thank you, Thomas. So I share. Okay, I share my screen. Everybody can see it? Can see it? Yes. Okay. So thank you, Thomas. Thank you for invited me to present k.LAB Landscape Matrix plugin into QGIS today. I prepared this presentation with Paul Meurice and Jacques Baudry, my colleague from the French research unit BAGAP. And it's something we are working on since a very long time, so we are happy to present it today. I will divide my presentation in 3 parts. First one is how to install technical issue plugin QGIS, and but I won't be very long on that subject today. Of course, if you have issues, you can connect. You can ask us by mail today or maybe tomorrow, and so on. The second part will be about what is k.LAB, what is it for, and the third step will be about how to calculate connectivity map using QGIS plugin k.LAB Landscape Matrix, the main subject of the presentation. I decided to make a tutorial step by step, slowly, simply, a bit complex, but in order to go together, going on and on, voilà, to be sure everything is understood. So for the installation procedure, very quickly. Just to remind you, maybe I assume you've ever done this, but so you have to download and install QGIS 3.10 only, because it's not working on other software of QGIS. Download and install Java JRE 1.8 minimum. You can open QGIS and click on plugins, manage and install plugins. Open the zip plugin as I assume you have downloaded, and click on install plugin. Then you have to get and copy the path to your Java bin folder. For instance, for me, it's C, program files, Java, GRE, blah, 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 bin folder. And under QGIS, you go here in settings, click and option. And in processing, you have providers. Here you must see k.LAB landscape metrics. And in the path Java exe here, you have to paste the path to your bin folder and add java.exe. For example, C program file, Java, GRE, blah, 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 bin java.exe. Okay, and after that you click on OK. Next thing, you have to check if you are under the Lambert 93 projection. That is the French projection, and on the project properties, and just check you have k.LAB landscape metrics available on your processing toolbox like that. Today, we won't see all the panel, all the functionality of k.LAB, but you know, just a first step. So, what is the k.LAB about? What is the purpose? It's a software to analyze cover maps, like the one that can be deployed and described as it was mentioned this morning, and to express biodiversity characterization, or like Thomas said this morning, blue and green infrastructures, so BGINs infrastructures, and TVB in French. It was developed at the INRAe BAGAP since the 90s by Jacques Baudry and colleague, and it's the integration. It integrates concept of landscape ecology, such as heterogeneity, connectivity, and it has been developed by research for research in the first step for thesis. And but now we are working to put this tool available for real land planning application, and that's why we are passing our software k.LAB into QGIS plugin. And this has been founded by two French regions, Nouvelle-Aquitaine and Bretagne. And it is developed by la Fédération des chasseurs des Côtes d'Armor. So first of all, we have to have a look on the cover map. Alors, you may have downloaded a start folder with that kind of information, and so the map, the cover map, is coming from the CESBio Ozoteia plus the IGN BD Topo. So those data are very useful because they are available on all the national French sites and freely. So it's very interesting to work with that kind of data, and it's quite precise enough. The area is about 15 kilometers by 14 kilometers, and very important, the pixel size is 5 meters in order to represent linear elements like hedgerows, like road, and so on. Here is a nomenclature of the map. You have summer crop, you have winter crop, grassland. We are working on grassland today. Hedgerows, forest, and other woods, water, urban, 3 types of road with different frequency traffic, high, middle, low frequency, and other crops. To do that in k.LAB, you just have to get your start folder and get the ZR, which is the cover map, and put it here on your layers. So when you do that, you have this something like that. And first thing we have to do is just to render this a bit more realistic. Click right on the layer properties, and here you have to load a style that is in the start folder as well, cover.qml. Okay, so now you can apply. Okay, and this is the same information, 5 meters precision. Okay, you can click here to be on the whole screen. Okay, so that's what we've just done. So the principle behind k.LAB is to calculate landscape metrics. It's the first thing we do with that software. We calculate landscape metric inside windows on raster map. And today, k.LAB only use ASCII grid raster map .IHC. And not if no other type of raster, only IHC. And the first type of analysis we can do is, and historically is the old one, is the grid principle. And the grid principle is to split the territory using grid size. And in each grid created, you calculate a metric. And with the help of all the pixels contained in the grid. And the result of this metric, that could be, for instance, the proportion of maize, or the proportion of water, or whatever. The result would be a pixel, just one pixel, on the result output. So not in the grid approach, the grid size, the window grid size, is the pixel size of the result. So to do that in k.LAB, you can use in the landscape metrics here, you can use a grid panel. And let's say we are going to calculate a Shannon with a scale of 100 meters. A Shannon is a Shannon diversity index, which characterizes diversity of values within the window. To do that, click on the input layer. Be sure you have clicked on the ZDA layer because it's a bug today. We really have to click on it, otherwise metrics won't be updated. So click on it, select the diversity metrics group, and select the SHDI metric. Here you can put the grid size. And the grid size is defined in pixels. So if you want a 100 meter scale approach, you have to think about your input layer. It has 5 meter resolution. So to have 100 meters scale, you have to put here 20 pixels. Okay, so it's a bit gymnastic, but voilà, 20 pixels. Let that, and here you can choose, using this button, you can choose where, the name of the output raster. Okay, so let's do that. Here, yes, ici is my panel grid. Yes, I click on the ZR information. I choose the diversity metric. And here I choose the SHDI. Here I set 20 for 20 pixels. And here is output. I will save it to a file. I have created my own folder, you know, tuto. And here's, let's say, grid 20p, SHDI. Okay, let's run that. So now Chloe is running. It has created a grid on the whole map, and for each of the grid inside, the window grid, it's calculating the SHDI. And now you can see here the results for this metric that appears here. Okay, so let's have a try to, here. Let's calculate with 40. 40 is, the double is 200 meter scale. Okay, and don't forget here to write a new name for the output. So it's the same map, the same metric, but with a larger scale. Okay, so it's running. The time consuming in grid is not dependent from the grid size. So it will take approximately the same time. Okay. So yeah, very soon finished. Yes, here is the result. So yes, 20, 100 meters, 200 meters. Okay, I remind you. So let's have a zoom to see what's going on. So black value are value where the Shannon is least, and yellow value where the Shannon is the most. So here is, for instance, here is the Shannon is important. And when I choose 40, big pixel, yeah, not very readable. So we did that. We have something like that for the SHDI 100 meters, for 200 meters, and we can go so on with, let's say, 1,000 meters. Yes, very big pixel. So we have two issues with grid principle, and two main issues. We lose the landscape gradient, and landscape gradient is very important when you analyze landscapes. We lose the continuity of landscape. It's not a smooth approach. It's very discrete approach. This is the value in this area. This is the value in this area. And the other problem is that pixel size and scale, so the analytic window grid size, are equal. So it could be very, very big at the end. So let's have a look at another principle, the sliding principle. It's another kind of analysis available in CLOE, and the principle is to displace a moving window with a displacement. By default, it's each pixel, and this window will be centered on a pixel. So it's something like that. You have a window, and you have a pixel, a central pixel here. And this window size is odd. Why it's odd? Because you have a pixel, you have a certain amount of pixel here, a certain amount of pixel, a certain amount of pixel here, plus 1 pixel. So it's odd, impair en français. And this window defined is used with a displacement. So this is one window centered on that pixel. You have the displacement, and you have this window. So in the first case, the analysis is those data, and in the other case, the analysis is analyzing those data. So there is an overlapping, and this overlapping is very useful. But let's do that on QGIS. You select sliding panel, you select the same Zeta input layer, the same diversity matrix, SHDI, and here you choose 21 this time because it's odd, and an output raster, of course. Let's do that. I choose the Zeta information, raster input map. I choose the SHDI. here 21 pixel, and as output, yes, sliding 21. Okay, don't forget anything. So the first thing you have to notice is it's a bit longer. Of course, it's because of the overlapping. For each pixel, a window is centered on it. Everything is calculated. Yep, it's done to the output, and up a little, just a little displacement of 1 pixel, and it's going on and on and on and on and on in all the map. So it's a bit longer, and the more the window size will be big, and the more the time consuming will be. Okay. So we have to be patient, but we'll see it's a bit useful. Just have a look on the. Okay, it's going on. Is it okay or not? It's working. It's important to understand it's a long analysis. Okay, it's finishing very soon. Okay, we have it. And this is it, the sliding window with 21 pixels. So it must be comparable to this. And maybe Zoom will tell you the story. Look the difference. So now you can see that landscape gradients, landscape continuity is back. And that is very, very useful and more readable. So we have that for 100 meters. We have that for 200 meters. We have that for 1,000 meters. And what you have to understand that is that for this part of this little zoom of the input map, which the pixel size is 5 meters. Here you have green windows. Here you have sliding windows. For the scale of 100 meters, you have here a pixel size of 100 meters, and here a pixel size of 5 meters. Here you have a pixel size of 200 meters, and here 5 meters. The same size as the input raster map. Same information, but just to be sure to understand, both grid and sliding windows output are analyzing the metric on an analytical window, both. But in one case, those windows are discrete, there is no overlapping. And in the other end, with sliding window, the overlapping can express surrounding information of surrounding one point. This is the concept. So sliding windows get the landscape gradient back, and the second advantage is that pixel size and scale with the window size are now independent. Someone has his mic. Can you? Okay, thank you. So that's the first part I wanted to show you to really understand what is sliding and what is grid, and why it is so powerful to use sliding information. So maybe Thomas, there is a question about that part. And if not, I will go on and go on the core of the subject today.
There is no question yet in the chat live. I think it's quite clear.
Okay.
So, okay, there is just one question. Is it possible to use k.LAB with other SRC? I think it is about projection file. For instance, to analyze map from another country.
Yes, it's possible, but it's just a little trick that when the output is generated, there is a projection file that is generated at the same time, and this one today is just the Lambert 93 projection. So you have to go and replace that file. That's the only thing you have to do. But in the future development, we will take the projection of the input raster to give it at the output. So it will be the same as your projection, your preference projection. Okay.
Okay, that's clear. Thank you.
So I go and how to characterize connectivity map. Oh, it's a good question. And it's in k.LAB a three-step method. We have first to define habitat suitability map. We have to define permeability map. And note that these two steps are made in parallel, so they are totally independent. In some tools or case, you have to define the permeability map as the inverse of the habitat suitability map. It's not the case in k.LAB. You can create both with their own logic. And once you have the two, you can calculate connectivity map. So that's what we are going to do. And first, of course, how to define habitat suitability map. Well, to do that, we are going to use a virtual species, an ecological model like a butterfly. Okay, it's just an exercise, of course. So let's define the habitat of this butterfly is grasslands, but not all grassland. Only grassland which are surrounded by at least 14% of grassland in a 250 radius buffer. Okay, and the permeability will be defined as difficult to pass through woody elements. You know that type of species cannot go through, with difficulties. And the dispersion distance will be very low, like 100 meters. So let's do that. So first, define the habitat suitability map. So the sentence is grassland which are surrounded by at least 40% of grassland in a 2050 meters radius buffer. So surrounded, sliding window. It must be like an automatic reflex. And at least 40% of grassland, so the metric will be the rate of grassland. And grassland is in our nomenclature we used as the code 3. Okay, it's the code we put on the nomenclature. So we can use the k.LAB metric PNV3. P is for proportion of number of value 3. And in a 250 meter radius, so the radius, so yes, we need not the radius, but we need the wall size, the diameter. So multiply by 2, 500 meters. As my pixel size is 5 meters, so 100 pixels. But the window size must be odd, because sliding windows are focused on one single central pixel. So window size must be 101 pixel. So the problem is here you can notice just just before we made a test with 21 pixels, it was a bit long. So now it's 101 pixels. It will be very long. So this is a Chloe trick you can deal with, is to define a larger delta of displacement, not each pixel, in order to save calculation time. And you can also interpolate approximate value for uncalculated window in order to have an output raster with the same size as the input raster. To do that, select the sliding window, select the cover map, the input cover map, of course. In the value type of matrix, put here PNV3, window size 101, and in the advanced parameter, you can choose here delta of displacement, not 1, but 10. Why 10? 10 because it's not something very very sure, but what we observe with our practical data and test is that when you choose 10% of the window size, you don't lose on the overall approach. You don't lose the landscape gradient. You don't lose information. You have approximately the same map. So 10% of someone is 10. Okay, let's say 10. And you can click here to interpolate values in order to calculate windows, to interpolate values that hasn't been calculated by the analysis. Let's do that with Chloe. So here I can select sliding, the zeta. Okay, value metric. Here you have PNV3, proportion of number of value 3, the grassland. Window size 101. And in the advanced parameter here, delta of displacement 10, so every 10 pixels, and you can interpolate values. Okay, output raster. I say grassland rate 101. Okay, let's run that. So it's still a bit long to calculate, but it's more quick. It's quicker than if you do not set a larger delta of displacement. So here the analysis is focusing the analysis on one point, getting all data on the surrounding map, calculating the metric, and after that, the displacement is not 1 pixel, but is 10 pixel, and so on. And all the value between have been interpolated. So yes, finishing very soon. Okay, you can close that. So here you can see a very good approximation of the rate of grassland in 250 radius buffer. Okay, so we have the cover map and we have the results. So it's not enough to define habitats, because in the sentence we also have grassland only, which are surrounded, grassland only, and 40%. And as the PNV3 metric is a normalized metric from 0 to 1, the threshold of 40% will be defined as superior to 0.4. And another Chloe trick is to use combine panel. It's just a raster calculator to combine multiple maps to a single one using an adapted formula. So you choose a combine panel here on the util, and you have here as input raster, you have to click on it and select the two which are necessary for the formula. And next here, you can click here to open the panel for the formula. And here you can see that the rate of grassland have been renamed as M1, and the cover map has been renamed as M2. And those names will be used on the formula, which is, if we have at the same time and M1 superior to 0.4 and M2 equal 3, 3 is the code of grassland in M2, so in the cover map. If we have both, so open the brace, you can say, yes, it will be an habitat. It will be an habitat. I say habitat is 1. I could say habitat is 4 or nothing or else, but I define that my habitat is 1. So, okay, it's 1, and other else it would be 0. Let's do that on Chloe. So the combined panel is here. Here you have to to click and select, okay, the grassland and the cover map. Here you have to be aware of the name of the two raster you need. And let's write the formula. If hand, open parenthesis, M1 is superior to 0.4 and M2 equal, double equal, to say equal, double equal, I said 3. Close the parenthesis 2 times, open the brace. So here I put the code of the habitat, I said 1. Close the brace, else 0. Okay, so now I can save this into habitat, grassland. Let's run that. It's something that is very it's quite quick, because it's something that it's analysis that take only pixel to pixel and write an output raster with that information. So it's quick. So this is the result. Okay, so let's render this a bit more stylish. Okay. You can double click on it, or you can click right properties, go to symbology here, and here choose paletted unique values. Just click on the plus button to add one information, and here say, okay, the information I need is a 1. 1 is for habitats. And let's say the color is a wonderful green. Yes. So yes, those are habitats I wanted to describe. And if you zoom on it, you can see that not all grassland are in habitat. Only grassland that are on area where where there are enough grassland in the surrounded landscape. Okay, you can see. So only grassland are selected, only in the good area. So we did that. We render the style a bit better. We have that. We have that. We have made a zoom to be sure not all grasslands are in habitat. Okay, so now, second step, define a permeability map. And the permeability is defined for vital species, the butterfly, as difficult to pass through woody elements. Okay, but what is permeability first? Permeability is how easy it is to move through a part of the landscape. Okay, so we have a landscape which is defined as a raster, so it's pixels. Okay, so how difficult is it to pass through my pixel? And I define too the friction as the exact inverse of permeability. Okay, and I speak about friction because even if in my presentation I speak about permeability map and so on, for real it's friction map. Be aware it's the exact opposite, but anyway, it's the same concept if you inverse it. So in a pixel with a friction value n is n times more difficult to pass through. So one is unicity, it has no effect. A pixel with value of friction 1, you can go in it just like if there were no friction. Large values are pixels difficult to pass through, or even barriers if you put a large value of friction. And 0 can be defined as corridor. So 0 is a pixel that don't take you any force, any difficulty to pass through. So to do that, the permeability map, to define it, we have to translate. It's a proposal, of course, but it could be a translate of the cover map, the input cover map we used, to a friction map. And this friction map is defined in the friction.txt file in the start folder. And I put this. I put summer and winter crop as one, so butterfly will pass with no problem. Grassland are corridors. Hedgerows, forest, and other wood elements have 10 value. It's even stronger, 10 values. It's 10 times more difficult to pass. Water 1, okay, can go. Urban and road high frequency, it's difficult to pass. Middle frequency, a bit less, but it's still difficult to pass. Road with low frequency, okay, you can pass. And other crop, I put a middle value. So to do that, to create that kind of permeability map, that is the exact translation of another map, and in that case, the input cover map. A k.LAB trick is to use search and replace panel to replace values on a raster. So to do that, open the search and replace panel, select the ZDA cover information, and open with that button, go and choose the friction.txt file. Once you have that, you can read values from input ASCII, which will update the values here, which are the value of the nomenclature. Select the friction that is available in the friction.txt and apply CSV map to update the new values. Okay, let's do that. Search and replace, the input map, the CSV file. Here, by default, it's only CSV. So to see TXT, click on TXT. And it's not here, of course, it's here. Friction.txt. Okay. Read values from the input ASCII. So this reads the values here and put them here. So select the friction value, friction column, and apply CSV. Okay. Everything is updated. So now I can save this to a file and set permeability grassland, for instance. Let's run that. As combined panel, it's quick because it's only a pixel to pixel analysis. Okay, I have it. But let's rendering it a bit more practical. Here you can select palette unit values, random color you can choose, for instance, magma, and invert the color ramp and classify values. So 0 value will be yellow, and strong value of permeability will be black. Of friction, excuse me, of friction will be black. So the permeability is the exact opposite. So here I have high value of permeability, low value of permeability, low value of friction, high value of friction. But let's speak about permeability. Okay, I can have a zoom on it just to see what is going on. Okay, so it's really a translation of my input cover map, just a translation. Okay, so we did that, we have the permeability map and we zoom on it. So now we can calculate a connectivity map because we have habitat in one hand, you have permeability map in other hand. So now we can calculate connectivity map. And the Chloe trick is to use a distance panel to do that in order to calculate a functional distance panel, a functional distance, excuse me, in order to characterize connectivity over habitats in landscape. The principle is to create a functional distance map as each pixel of the output raster is characterized by the least cost path distance from the nearest habitat according to permeability to friction map. Okay. So to do that, choose here the distance panel. Here, this time don't use Zeta, but use the habitat we calculated before. Here you have to put the value of habitat that are in this map. So I said one value, so it's 1. And here in distance type, don't use Euclidean distance, but functional distance to take into account permeability we define. In the friction file, you can here select and put the permeability we have created. Do not, at the moment, do not use the maximum distance. Let's this like this, and select an output raster, an output ASCII. Yes. Okay, let's do that. Distance panel, habitat is input, and my value of interest in the input raster is 1. I choose the functional distance, and here I go and select my permeability that we have just created. Yes, this one. I let this like that, and here I say connectivity grassland. Okay, let's run that. So here the calculation is kind of diffusion from habitat, and according to permeability, it will give a value to all pixel. What is the distance for this pixel to the nearest habitat according to the permeability? Okay, finishing very soon. Yes. Okay, and this is the result. Not very beautiful, but this is the result. And if you go here to select to view the values of the map and click anyone here, for instance, you have 135. So the pixel I click is 135 equivalent meters to an habitat. So to view this more readable, click here on the properties, and in the symbology, you can choose single band pseudo colors. And here you have the minimum value you want to take into account. And here you have the maximum value you want to take into account. So let's say 100, because we said that our butterfly can disperse to only 100 meters. And in the color ramp, green is good, it's a good ramp, but just invert it to have a value close to habitat very green, and the more you go from the habitat, the more white you are. And let's say that large values of distance are not white but transparent. Okay, transparent here. Apply that, and this is the result. This is the distance information we can calculate with Chloe using this habitat and using this permeability map. So, okay, I put the layer of the habitat too. So to me, it's not satisfying, and to us, I'm sure for you too. Too few habitats are connected, and we know from observation that this is not accurate enough. There is a flaw in the model. This is a wrong model. We cannot see here any connectivity, any corridors, any connectivity. So no, it's not the good. We have something. We have a problem with the hypothesis. And especially, we have to refine the hypothesis according to the permeability map. So we said permeability difficult to pass through woody elements, but can we say that woody element can be corridors, because there are grassy strips along woody elements? Okay, butterfly cannot go with difficulties passing through woody elements, but there are here grassy strips that can be used for species like butterfly to go and go. So what if we say, yes, we can go further and update the permeability map, and in that case, and except where there are roads or where there are urban areas. Okay, let's say that. And to do that, so we have the objective is to put a zero friction, corridor friction, to code a code to pixel close to woody element, but not on woody element, of course, and not on urban, road high frequency or road middle frequency pixel, in order to express new corridors in the permeability. To do that, we have two solutions at least. Solution one is using the distance panel to woody element, but let's use the solution two using a square sliding windows, very little one, 3 by 3, which calculates the proportion of woody element. Okay. So to do that, the first step is to create an alternative cover map in order to group woody elements. Hedgerow, forest, other wood will be redefined as wood, and to group urban, road high frequency, road middle frequency, 8, 9, and 10, that will be refined as urban and road. And to do that, once again, use the search and replace panel. So you take the search and replace panel, you take the data cover information, and here you have to click on read values from inputs ASCII in order to update values. And here you can put new values for the old values you want to change. Values that won't be updated won't change. So, for instance, water 7 will stay water. Okay, let's do that. Let's do that. Search and replace panel. Zeta cover map. I read the values from the cover map. They arrive here. And let's say, okay, so I say 4, 5, and 6 become 4. And 8, 9, and 10 become 9. Become 8, excuse me. The output cluster ASCII is, well, let's say, Zeta alternative. Yes. And I run that. So now the analysis is creating a new cover map in order to be able to calculate a new thing on it. Okay, so we have this one, and just to be comparable with the old one, you just have to click right, properties, and style, and go and load the style I put in the start folder, cover alternative. Okay, apply that, and now here you can see the new nomenclature. So this is it's not a new cover map, but it's a cover map we are going to use now. Okay, so next step is to detect local wood. Yes, we want to know where there is wood not far from here. So, in order to create those edges. So to do that, use a sliding window. Select the alternative this time, and select the proportion of woody elements. So now it's not 3, it's 4, the 4 code in the nomenclature, PNV4. And this in a very little window, 3 by 3. And in the advanced parameter, we have to choose a square window shape, because by default, Chloe uses circular windows. So now, in order to integrate not only cardinal neighbors of pixel, but also diagonal neighbors, you have to select a square shape window. Let's do that. Sliding window, c'est the alternative. Be sure you click on it. Select value metric, and here the proportion of number value 4 for my woody elements. Window size 3, it's okay. And in the advanced parameter, select square window. Okay, so my input raster will be, let's say, local wood. Run that. Sliding window with 3 by 3 windows. It's not a huge window, so it's quite quick. Do not make a displacement here. Let the displacement of delta of displacement to 1, because here we really need to have information, very precise, very accurate information for each pixel. Do I have a wood in my local information, in my local window? Okay, it's very important to not have a displacement here. Okay. So this is a local wood, just a detection of wood elements. Huh? You can see it. Okay. So, yes. So the third step now is to combine information to update the permeability map, a new permeability map, for taking into account local wood edges. Okay, so to do that, it's a combined panel. A combined panel which use the data local wood we just created, the old grassland permeability, and the new cover alternative. So you have to check those maps. To select the formula, you have to click on here, and here, be very careful of the rename of your file, because it's not if you displace here the order of the different raster, you will have here a different naming. So be very careful on the naming, and do not apply the formula like it is. No, very be careful of the naming. So now we have M1 for the local wood, M2 for the grassland permeability, the old one, and M3 for the cover map. And the formula here is, if we have at the same time the local wood superior to 0, so we have wood in the surrounding space, and the cover is not exclamation point equal is equal means not. So cover map is not wood, and cover map is not 8, you know, it's urban and road. So you will put the code 0 to explain corridors on the new permeability map. So it will be a corridor, it will be 0. Otherwise, it will be the old permeability value. Just to click M2, because it's M2 permeability here. Okay, let's do that on Chloe. So I use combine panel, I select the old permeability, I select the local wood, I'll select the alternative. I here go and see the naming is not the same here, you see. So if we have hand local wood superior to 0, the cover map M3 exclamation point equal 4, it's not a woody element, and M3 exclamation point equal 8, it's not urban and road pixel. Close the parentheses, close the parentheses, open the brace. This will be 0 code. This will be corridor, new corridor pixels. Else, just put no, not M2, M1. Just put the old permeability map. Okay, so now I have to save this to my new permeability. Let's say permeability alternative grassland. Okay, run that.
Okay, while you are processing your operation here, there is a question from Selena, and she's asking, how do you parameterize habitat suitability or quality if you don't have to focus on a particular species?
It's a difficult question. I remind you, I'm just a software engineer, and my purpose is to bring you some tools to manage your data and your hypothesis with your ecological model. So as I know, as far as I know it's possible to have what we call in French espèce parapluie, species that represent a larger group of species. So if we model this species, you can say by boule de neige, you can say that other species are also implied in that compartment. But if you have two species very precisely defined as completely different, you have to define habitat, define permeability, and so connectivity separately for the two species. Okay, and maybe after you can see where it's relevant for one species, where it's not for the other, and maybe you have some space on the territory where the two species are present, and other space where other area where there's just one and not the other, and so on. Okay.
Okay, and maybe you won't show us how to combine this kind of two connectivity map, for instance, but I think you may have already think about how to proceed and to combine this kind of multi-species analysis. Am I correct?
Yes, yes, but it will be very hard to precise this today, because
okay.
I need some more material to show you something like that, and I just encourage you to contact me after.
Okay, so Chloe does that, but it is not in this practical.
No,
okay,
I'm sorry for today.
No, it's okay. Don't worry.
So here we have the new permeability map we've just generated. Just for the rendering, we have the old rendering of the old permeability. Just click on it, style, copy style, and you can click on the new permeability, style, paste style. So now you can really compare them with the same style. So if you zoom on it, yes, you can see what happened. You can see that woody elements have been surrounded by a corridor, but not on roady elements or urban elements. Okay, it's exactly what we wanted. So now, yes, we have that. So now we just have to calculate a new connectivity map, taking into account this new permeability map. Okay, so the distance panel. You can click on habitat grassland. The habitat is the input layer. Okay, remember that. One value is the value of habitat. You type the functional distance. You put here. You set the new permeability map we just created here, and this will be the new continuity, the new connectivity map for today. So it's a distance panel. Habitat grassland, one value for habitat, functional type distance. The friction is the new permeability alternative grassland. Yes, this one. And the output is connectivity alternative, let's say. Run that. So once again, each pixel will be characterized by its least cost path distance to the nearest habitat according to the new permeability map. Okay. Okay. So it's as beautiful as it was, and select the old connectivity. Click right, style, copy style, and now on the new one, style, paste style, and now is a connectivity. The connectivity that could be very more interesting than the old one, because here you can see with 5 meters of precision that there is a corridors through landscapes. So that was the main purpose of the presentation today, but we can go further with that kind of analysis, and there's just one step I wanted to show you today. Just one step further. So yes, habitat are now connected through landscape element. So I don't know if it is a good model. Again, I'm just a software engineer, but the tool allowed you to test and set value parameters, data. Of course, if you change your cover map, you will change the result as well. So you have to test and be careful of all your parameters. And just what Chloe is about is to help you to view the results. Okay. So for instance, here, if now I don't say, oh no, my species don't go from 0 to 100 meters, but only, let's say, 17 meters. Yes. So same artifact. Okay. Apply. Oh yes, it's more like that because I know that here and here it's not connected and so on. You can have something like that as an approach to precise what kind of connectivity you want to characterize. But anyway, sorry. Yes, it's okay. So let's step for today. How habitats are clustered. So now we have habitats and a connectivity map, but we don't know, for now, we don't know who is connected with who, which are habitats that are in the same clusters, in the same aggregate. So what is the cluster panel about? So here you have to select the habitat. It's exactly the same parameter as the distance panel. You have to select the habitat crossland here, select the one value of the habitat, select the functional distance, put here the permeability, like for the distance, like for the connectivity. But here you have to put the maximum, the threshold. So here you have to put 100 meters if you want to test 100 meters. You can put a minimal area for clusters, let's say 0. And here you can put the output raster. It will be the last step for today, but I think it's interesting to see what it gives. Okay, functional distance in meter 100. The friction is a permeability alternative, the last one we generated. Minimal area 0, and the output raster, let's say cluster grassland. So now it's calculated which cluster are which habitat are together according to the permeability. Okay. Okay. Wonderful, isn't it? So to render it more beautiful, paletted unique values, classify values, and delete the 0, 1 because it's the background of the landscape. Apply that and here you have the clusters of the landscape. So if there is the same color, it's the same cluster. So all habitats in, let's say, pink are connected together with at least one pass. The green one are together, here they are together, and so on. So here was the final information I wanted to show you for today. So you can really express some very precise connectivity information and with a precision of 5 meters.
Okay. So thank you, Hugues. There is a question. I think it is related to other application of connectivity calculation. Axel is wondering if there is an option in k.LAB to calculate graph theory-based metrics, such as the probability of connectivity.
No. The graph theory is not in k.LAB. Okay. Because we have a different approach. There is two things. First of all, I think the graph theory can be viewed as the next step of that kind of information, because here you focused on which are the habitats and how they are connected. So you can set a value of the node between the arc in the graph theory. Okay. And in the other end, we have ever work on the different approach of is in my aggregate, in my cluster, are habitats really strongly connected or not? Which habitats are more connected than the others? So and so on. So we have begun to work on that kind of calculation, and it's not available in k.LAB yet.
Okay, thank you for your answer. I think your k.LAB software is pretty nice, even if you are mentioning that you are not working on specific species or so on. But I think it is really user-friendly in order to make some very concrete maps that are meaningful for stakeholders. And I think it is in the line with what José has shown to everyone this morning about the use of this kind of map afterwards with decision makers. So I think it is really interesting to see where are the clusters, the size of these clusters. These are some small and disconnected or connected clusters together as well. And no, I think it is really efficient. And well, it was the aim of this tutorial in order to make people able to use directly software on their own, and then maybe to go further into detail and try to combine different umbrella species or multi-species analysis like this one. And of course, if some of you are interested to go so far, please contact Hugues. He will be happy to help you in this use of k.LAB software. There are still times for questions if some of you are wondering other questions. But anyway, Hugues, they are just thank you for they do thank you for your talk, because it was clear, I think, very practical. So there is a question. Someone she's wondering if there is a list of papers that is using your software yet.
I don't have the list, but there are some theses that use a k.LAB approach, sliding approach. No, I don't have the list, but I think Jacques Baudry, my colleague, can give you such a list. And And last thing I wanted to say, because my other colleague Paul wanted me to say that, is we are still working on that software, and we are still developing some new algorithm and new concept. And for instance, we are working on the landscape of eco-landscape. We are developing, we are redeveloping the sliding window software algorithm in order to be very more fast, and so on.
But in terms of paper, I would say that maybe some are coming soon. So in a few months, so we will let you know if you are interested in. Right. I don't know if there is other question. People are, thank you again. I see that Stefano Balbi is on as well. I would just maybe, I don't know if you let me just share my slide, and we are maybe 5 to 10 minutes ahead the program. So I think maybe we could make a short break of 5 minutes in order to hold on technical issues, and then maybe we can go through the third tutorial. Maybe I should also switch on my camera. Where is my? Let me say. Okay, here I'm back. Well, do you want 5-minute break, or should we just go on?
I'm happy with whatever you decide.
Maybe we can do a short break, just 5 minutes, and we start just before 3. Maybe also I can give you the floor, Stefano, to check if there are some technical issue in order to use properly k.LAB before starting.
Yeah, no, what is important is that I'm sharing the screen properly and that you see my face, and the audio is okay.
I will give you the floor.
So I can start with the presentation, or should we do a break?
Okay, let's start at 3, just a little before 3. But if you need to check on technical issues, like if to download the right version of your software and so on, or if they just want to use the browser, maybe just check that with the participants. I don't know.
No. That's part of my routine from 3 on. I'm starting at 3 with that.
Okay, let's do a short break. But there is some, of course, Jose is interacting in the chat. These kind of maps have in fact to be included in further multi-criteria analysis for SCP approaches together with habitat and land use and land change dynamic, for sure. It will be helpful to define sustainable management actions, and even more when considering the blue and green infrastructure network, for sure. Okay, so let's do the break.
Yes, during the break. Sorry, Thomas, if just to use the break for filling the gap of silence. And yes, what I wanted to explain in the chat was to emphasize what I tried to quickly explain at the end of our intervention before, that it's not enough having the good maps about the distribution of any pattern in the landscape continuum. We can identify where are the habitats, we can identify where are the species, the areas with high suitability for the species distributions, but we need to know how the different patches interact and how they evolve in time. And with that information, we can put together structure and dynamics with, yeah, sorry, I put the video, the structure and the dynamics with the functioning. Only once when we know how are our patterns, which are the processes that drive that patterns and how that patterns evolve in time, we have the whole picture, understanding patterns and processes and function, to give the floor to Stefano, that now will tell us how we can include all that information within truly and well-done ecosystem service modeling, for understanding not only how things are distributed and evolve, but also how we can make use of that information for ecosystem service modeling, and in the last term, using the benefits for the provisioning, for regulation, or for whatever use we want to give to the landscape. So, well, just to the maps that you showed us now need to be included together with the habitat maps for understanding really how landscape function, and then to run subsequent analysis. Yes, for filling the gap of silence. Thank you.
Okay, good afternoon, everybody. I think I will slowly start my tutorial. I am Stefano Balbi. I am based at the Basque Center for Climate Change, and I'm an ICAR Basque Research Fellow. The Basque Center for Climate Change is participating in the ALICE project, which, as you have understood from the presentations this morning, is an Interreg project on the Atlantic area. And we are in charge of integrating the modeling approaches used in the project. in a way that basically everything that is produced by the partners can be used in an integrated modeling fashion. Sorry, I was reading the chat because they were telling me that my face didn't show, but now is I think showing properly. There is a little bit of delay between what I'm saying and what you see in the live channel in YouTube, so there might be 20 seconds lag. So I'm here to talk about k.LAB, a software that we develop in BC3. And I need to start by explaining ARIES first. So ARIES, nice, I cannot even, okay. ARIES stands for Artificial Intelligence for Ecosystem Services. It's a project that was born in 2007 in the United States with a fellowship from the National Scientific Foundation. And from 2012, this project is based in the Basque Country at the Basque Center for Climate Change. Also, in the last years, we had a lot of support from the Basque government and the Iker Basque Science Foundation. And this is where we are now. So artificial intelligence for ecosystem services. This project is about ecosystem services originally. Why? Because ecosystem services are one of the most complex issues to be modeled, because they are about the relationship between nature and human societies. So, for example, you have this schematic representation in this slide where you have nature on the left side and societies on the right side. And ecosystem services are the benefits that are flowing from nature to the society. And as you can imagine, we are enjoying so many benefits from nature, and all kinds of complexities can be considered in modeling ecosystem services. And so it's the typical case where basically we need a lot of knowledge to explain a very complex phenomenon. And this knowledge is very often is compartmentalized and needs to be integrated. So that's why the project was born with this idea of integration and basically using granular and modular modeling components to establish ecosystem services modeling workflow. And these are the words of the principal investigator, Ferdinando Villa. So the paradigm behind ARIES is to use technology to build integration and to break up granular customizable components to represent ecosystem services as they are. So how do we do this? We do this with one branch of of artificial intelligence that is not very much recognized at the moment. So most of us understand artificial intelligence as machine learning, which is basically the way of uncovering pattern in data, while machine reasoning is a completely different branch that uses semantics, so logical declaration and axioms called ontologies, which define concepts and the relationship between them, and then reasoning to link data and model using logical inference to automate their assembly into useful structure for computation. Basically, with semantics and machine reasoning, we are telling machines how to compose models from data and modeling components that are in need of integration. So ARIES is a project on ecosystem services, but in developing ARIES, we have in fact developed a technology for the integration of data and models. So what I'm going to explain today is the k.LAB software. It's a software stack and is, let's say, comprised of many features that I'm going to try to explain as much as possible. And the final aim of this technology is to completely change the way we do modeling. Instead of starting from scratch from our own desktop, to basically use a network of knowledge that is already available and which we can reuse. So the software stack, as I was saying, is quite, let's say, includes a lot of components. The most important one that I want to explain today is the engine. So the engine is the entry door to this networked software, and allows you to enter the network of knowledge of k.LAB. You have received the instruction to start this software in two possible ways. One is with a downloadable software, and one with a direct link in a web browser. So I will try to explain both today. With the engine, you connect to a node that basically, well, first of all, you need to authenticate and create your own user profile. And then when you are in the network, you are basically using many nodes of the network that can contain data and models. And then we have a user interface. So this is the user part. The part that you can actually see is the modeler. This is the part that I'm going to explain at the end of this tutorial. And the part where we will spend a little bit more time is the explorer. That is the user interface for people that want to use the modeling components without actually creating new models. So the type of use that the software allows is simple observation workflow. And basically this enables you to set a context of analysis and to type a query in a search bar. And this query is completely conceptual. So it's not querying specific data or models, but the machine, through machine reasoning, is able to link all the data and models needed to respond to that query. And for example, there you have an example of how the semantics is written in our semantic language. So you have, for example, the occurrence of pollinator is the presence of pollinators, and this is a required piece of knowledge to respond to the query on pollination. And this query is passed in the semantic network, and the machine is able to construct the computational workflow needed to respond to the question, and then produces the modeling output, which are both maps, but also written reports, so explained in a narrative way, and also the computational workflow itself, fully documented in a data flow like this one. We are going to see this in the tutorial. Because we recognize that this technology that we have developed is completely generalizable, so it's not only for ecosystem services, we have created a partnership for integrated modeling. This is the address. And basically, this is our institution for, let's say, guiding our collaborations with other institutions. Because we want to share this knowledge, we want to share this technology, and everything that I'm explaining today is open source and open access. And we want to keep it that way as much as possible. So, as I was saying in the beginning, ARIES stands for Artificial Intelligence for Ecosystem Services. Used to mean ecosystem services. Now we are rebranding ourselves because we have understood that everything that we are doing is much more than ecosystem services. So we are also doing renewable energy, marine spatial planning, natural capital accounting, freshwater ecosystems, and biodiversity. So the new acronym is Artificial Intelligence for Environment and Sustainability. These are our channels. So please contact us if you are interested in what you are going to see in the next hour and a half. You can find us on all the main social networks. If you have problems with the software, please write to support@integratedmodeling.org. So this is basically the structure of what I'm going to show in the next 2 hours, actually 1 hour and a half. So the introduction was this one. So now I will finish with the slides and I will start showing the software itself. The first part is how to get started with the K-Explorer user interface. The second, after that, I'll do a quick tour of the user interface itself. If you want to go deeper into the subject, I direct you to this link. It's a YouTube tutorial by Ferdinando Villa itself, so the principal investigator of the project. And after that, I will do a quick tour of our ecosystem services related models. Those models are published in a scientific article in Science of Total Environment in 2019. So if you want to have more details about them, please refer to that publication. After that, I will explain a little bit how we are able to further customize the user interface into thematic maps, into thematic apps. And this one in particular is about natural capital accounting. After that, I will give a quick introduction to the modeling user interface. So that requires a little bit more training. So I'm not going to cover a lot in this tutorial. But let's say up until point 4, you can try to repeat everything I'm doing with the online engine. Otherwise, everything else with the downloadable software from point 5 to point 7. Point 7, finally, are the models that we developed for the ALICE project. I will give you an overview of the work behind the models in ALICE Interact project. So this is the end of the presentation. Let me check if I have any message in the chat. I see a little bit messages here. Okay, I will stop checking the chat because it's distracting me a lot. So I will close it here and start with the software itself. So I have a little bit of problem with this part of the screen. Maybe I can go here. So let me start sharing again, please, the screen. Yes. Okay, so now you see, hopefully, the web page itself. It's integratedmodeling.org, get started. So here you can find all the basic information on how to get started with the k.LAB. And here you have the link to the software download. You have it for Windows, for Linux, and for Mac. So you received the instruction about how to do all of this before the meeting. So I hope you did some of the steps you were supposed to do. Otherwise, no problem. Well, supposing you have installed the software, you would have to launch it, and it will start, for example, from here. So the second part is actually to register. This is very important. So you need to go to integratedmodeling.org in the hub and then register here. In my case, I can log in, for example, and I can click in the profile section and download the certificate. This is very important because the certificate is what allows you to authenticate in the system. So the system knows who you are. And you can download it by clicking it. Well, I can actually when you click, if you have the end user license agreement, you just click and accept. And it's downloaded. Okay. So you have the certificate, you have your profile, you have the certificate. Now you can actually start the software. This piece of software is called the control center. And the control center, as you see, recognizes me, Stefano Balbi here, and I'm already authenticated. What you need to do in order to be authenticated, you go and you take the certificate where it was downloaded, and you just drag and drop it on this panel here. And then the system will recognize you, so you will have your username here, and then the groups to which you belong on this side. Now, the second part is, supposedly you are in this situation, you need to start the engine. So as I was saying, the engine is the gate to the network, the semantic web, and you need to click on this in order to start it. So you will see that this terminal window will appear, and then slowly the engine will go online. The engine goes online, and when the engine is online, we are ready to go, and we can use the client, which is a web browser, in order to access the K-Explorer user interface. Give it a little bit of time. So as I wrote in the instructions, you can download the software and do like I'm doing right now. Or for this particular training, we made available this link here, integratedmodeling.org/modeler, which allows you to log in with the same username and password that you have created in the hub. And you can access the online engine. So now I'm still using the software. The engine is online, as you see in the window, and I can use this icon here to start the K-Explorer in my default browser. Now my default browser is, in this case, Mozilla. When it starts, I'm welcomed with this tutorial, which I suggest you to scan when we are done with this tutorial, because I think it's very useful. It contains a lot of information, especially the cheat sheet here. There are many commands that you can try to use and repeat. But for the moment, I will close it. And I am in a situation where basically looks like a normal map with this search bar and an elephant in the search bar. So let me just show you that if I do this in the online engine, so username and password, I log in, and I'm exactly in a similar situation. The tutorial starts, and I'm in a map like this. Perfect. So let's assume that we are, all of us are in this situation with the map and the search bar open in the default browser. Supported browser are Chrome and Mozilla, so mind that, please. This is K-Explorer, how it looks like at the beginning. So it's just a simple, looks like a simple map. You can actually change the background map, and I'm using the minimal. I can use OpenStreetMap. I can use all of these layers. So what do we do now? Well, it's important that we realize this is not a simple map, but this search map actually allows me to introduce my queries. For example, well, this tutorial is would have been based in REN if we were doing the school in presence, but we are not. But anyway, let's try that and type something here. So as I type, the system suggests possible solutions. For example, in this particular case, I'm typing elevation. I can type eleve, and this is suggesting only elevation. I just click enter and enter again, and the elephant, the ball of the elephant, as you see, starts spinning and is giving me an answer. And the answer is the elevation map in the region in the map where I am. So you can see that I can click on the map and see the values, but I can also click on the layer itself and see the histogram. I have a lot of information here, the number of cells in the map, and the total area in square kilometers, stuff like that. So this is one possible search to do. And I can search many things like slope and all the geographical variables that you can imagine. But this is much smarter than this. So it's not a way to query data only. It's an actual model. So I can do the same. Instead of searching for elevation, I search for normalized, and I select it, and then elevation. And again, click. So the system now has done something that is similar to before, but it's also very different. Instead of giving me the map of elevation, it has given me the map of normalized elevation. Now this seems very simple maybe, but this calculation has been done on the fly, well, after I entered my query. So in the data flow, I can see what this what the system has done. So the elevation information has been fetched online through a web coverage service. And this is a global layer of elevation with a resolution of 90 meters. The original data is 90 meters. And then this information has been normalized. And so the output is this one. I can check again the histogram. Now you see the histogram is different. It goes from 0 to 1. It's completely different than before. And I can download this data if I want. I can browse over the layer and click on this and download it as a GeoTIFF or as an image. But it is important to understand that the query has been resolved by first looking for elevation. So this is the original data that was taken, and then computing a normalization on the elevation data. So this is the first example that I wanted to show you. One important message here is to understand that this data is not in my machine. These data are served online. So when I query in the search bar, I'm actually accessing to a web of knowledge, of scientific knowledge, and that we call a semantic web. because this knowledge has been identified and formalized in terms of semantics and ontologies. I was searching for elevation with the small cap, but if I, for example, I can reset the context and go to a particular region, like Ile at Villain, which is the region of Rennes. So you see, now I have the context in front of me, and then I can type elevation again. And this is completely different. So what I've been doing is to search for a context, a spatial context, by starting with an uppercase and then clicking enter. And then with the lowercase, I searched for elevation, and now I have elevation in the area of interest. So a couple of things that I didn't mention is that in this icon, I have the spatial resolution, and in this icon, I have the temporal resolution. I can change both of them at the beginning of my analysis here. So I can set precisely at which resolution I want to work. For example, well, the system, when you are in the default situation, is giving a default spatial resolution, and I can change it to, for example, 150 meters. The same goes for the temporal information. So the default is the present time. I can definitely go and change, for example, 2018. And if I want to have multiple years, I can change them at this stage. Yes. So this is how to set the context. So all the queries that I'm doing are completely conceptual. I'm not looking for a specific data or model, but I'm looking for a concept here in the search bar. And this concept is resolved by the machine through machine reasoning. And the machine is able to match data and models, to combine and assemble them in a way that matches the context of analysis. And the context of analysis is precisely this. Can be let's say, the spatial context and the temporal context, but also their scale. So the resolution, the temporal and spatial resolution. One more example that I wanted to show you is there are operators in the system, like this one, type of. So I can just click enter here. And now, for example, I can click geoformation. So if I search for type of geoformation, the system again is taking elevation, but this time is giving me another model, a little bit more complex than normalizing everything. This is actually classifying all the landscape in terms of type of geoformation. So flat type, peak type, slope type, and valley type. So what is different from before? This is the data flow. Well, again, I take the basic information is elevation. This is classified in terms of terrain morphology, and then giving me the final output: flat, peak, ridge, shoulder. Now, this algorithm has been taken by scientific publications and implemented by us, but we didn't invent anything here. Next example is that so far, so I can reset the context again. Let me go again in our context here. So far, I've been showing what we call quality split, basically spatial variables. I can actually search for concept. Like, for example, I can search for city. And in this particular case, there is only one big city, which is Rennes, and is here. Now I can also search for towns. Sorry, everything has to be singular when you type in the search bar. And as you see, the towns are many more. So the city is only Rennes, but the towns are all around. And another thing that I wanted to show is that you can do operation on these objects that have been identified. So for example, you can type distance. The system suggests the operation distance to. I can search for town, distance to town. So the town have been identified already. So the distance to town is quite easy to compute for the system. So this is the Euclidean distance from every point to every possible town in the context of analysis. Remember, the towns were here. And this is computed on the fly while I'm basically in response to my queries in the search bar. Now, I wanted to show you how the system is very smart. I was mentioning about the context dependency. So I reset the context. I put the minimum up because it's the lighter one. And I can go around everywhere in the world. So all the queries that I've been showing until now, you can do this everywhere in the world. You can zoom in, zoom out. You can search for places here. Remember, start typing with uppercase. But for example, let's go to Gibraltar. So to show you how multi-purpose can be this system, I can, for example, I can search for restaurants in Gibraltar. Sorry, lowercase. And I get the restaurants in Gibraltar. But this is not actually what I wanted to show you. What I wanted to show you is that the system is intelligent and knows that the context defines the answer in the way that is assembling data and models. So for example, I can search for land cover type here. And this is land cover type. I just click. Now this is taking a little bit of more time, but remember that I can always go and check in the data flow what the system is doing. And what the system is doing is very smart, because basically I'm in I'm in a very special place here. And so around Gibraltar, you have Morocco on the southern part, and then you have Spain on the northern part. And as you know, the land cover type, there are many land cover types. In this particular case, the system is picking Corinne for the European side, and then CCI for the Moroccan side, and is combining the two. So I can click in all the points and see what is the land cover. Broadleaf forest, non-irrigated arable land. You see that, for example, here you have high density urban. This is the way that Corinne classifies artificial surface. But in CCI, you only have artificial surface. So this example is meant to past the idea that all the searches that are done in the search bar are completely conceptual, while the data and the models that are matched to respond to those queries are left to the machine to select. It's everything is automated using artificial intelligence, and that part of artificial intelligence that I was mentioning before. So semantics and machine reasoning. And the knowledge that appears in my browser is belonging to the network of knowledge that we have put in place. So far, all the nodes that are serving the data are managed by us, but we are actually making it available to every institutions that want to join this way of doing modeling, integrated modeling, and this philosophy. So far, I think I have shown a little bit of the K-Explorer, and I am following quite well what I wanted to show you. I don't know if there are any questions, please. You can write the questions in YouTube, or you can also. Yeah. So at this point, I think I will pass to artificial intelligence, to ecosystem services, because basically this is what everybody expects to see. So resetting the context here with an X, and I can go anywhere in the world. Let's go back to France, where the school should be. So the technology that has been developed for developing models for ecosystem services so far we have developed some predefined queries. So basically the idea is that the search bar itself is not super intuitive. I mean, you can search many things here, but it's difficult to arrive to a query related to ecosystem services. So we have prepared predefined queries, and that you can access them just by clicking the spacebar. So by clicking the spacebar, you have these multiple predefined queries, and these queries are divided into thematic chapters. For example, carbon storage, pollination, flood regulation, outdoor recreation, sediment retention, and many others. So the models that we have published and are endorsed are those with this this icon. Other models are in development. Other models are very experimental. You can just browse around with this icon and see their meaning. So for this particular example, I wanted to show you the value, let's say the pollination models. So the pollination models are meant to give you an assessment of the importance of pollination, and you can run all these models everywhere in the world. So for example, let's click a little bit here in the center of France. I just type the space bar, and then I click on net value of pollination, and I press enter. Now, this query is a bit more complex than the queries that I've been showing until now. If I click in the data flow, you can see that the way the system is responding to my query, well, it's a bit more structured. So there is the first part, in this part, that basically is using land cover to understand the probability of flowering and the occurrence of pollinators. They're nesting mainly. And then there is one part that is related to the occurrence of pollinators due to weather conditions. So this is more climatic variables. And this part here is more related to the need for pollination from crops. So the system has already computed everything. And I can see that, for example, the final output is the net value of pollination. It's a lot of red here. So I need to explain a little bit what this model is doing. This model is basically giving you a positive number when the supply is more than the demand for pollination, and then a negative number when the supply, when there is a deficit, so the demand for pollination is higher. So apparently this part of France, there is a lot of demand for pollination. I think there is a lot of agriculture all around here, but there are only few parts where this demand is satisfied. So these are the white parts. The green parts are the parts where there are more pollinators than needed. So again, the model is, this particular model on pollination is resolved in this way. And all these components here are used to assemble the final answer. So for example, this set of global models that we have produced are able to give you a response in everywhere in the globe using global data that we have made available. So basically the user doesn't have to do anything apart from using the right way to query the system. And some of these global information layers are particularly coarse. Like for example, this one is about the demand for pollination from agriculture. So this is using a 10 by 10 information layer. It's very, very coarse. We are using the land cover to filter the agricultural vegetation. But I mean, the default information that is used here, so the global one, is quite coarse. And
there is a question related to this data set available globally.
Yes.
Some people are, Selina is wondering if these are applicable on area with scarce data, some like in remote area and so on, but I think you already answered to that. And Benjamin is also wondering if there are some kind of standard deviation of variance values that could be derived from your different ecosystem services index.
So the first answer is for Selina, that we are providing global information layer to resolve all these main queries. So the ones that you can access to by pressing the space bar. All of these models are basically, they have a default answer using global information layers that we have made available. But a user, an advanced user, and then I will show you in the second part of the tutorial, can substitute any of the informational artifacts that are basically explained here. So any part of this model, any part of these components, any of these bricks, can be changed with the local information. And then I will show you later how to basically annotate semantically your local data. So this is the first answer. The second answer, I think, the question is related to, so far these models that I've been showing are deterministic models. So they have a number in every pixel. And for example, in this particular output, you have a number in every pixel and one number that goes from -1 to 1. So this is a deterministic model giving you one number as an output. There are other models like the one that I will show you later, like Bayesian networks, that allows you to give multiple outputs. So for example, the output of a Bayesian network is a probability distribution. And in that case, you can produce map with the mean values, but also with the standard deviation. So yes, both are available. Okay, so this is for pollination. I can try other models like, for example, vegetation carbon. This is implementing the IPCC official methodology.
Maybe you can complete your description and with one example of where you get these models, where you get this information from the IPCC or any other publication.
Yes, I will show you
later. Okay.
I'm coming to that. So this is the data flow for the carbon model, and the carbon model is giving you the vegetation carbon mass in every point. So I can click, and this is given in tons per hectare per year. So good question. How do we implement all these models? Well, I will show you later in the modeler how we implement the models, but the model themselves, so this is a new part, a new feature that I didn't show until now. For this particular predefined queries, every time you run them and the model is completed, they are producing also a report in a narrative format. That is also produced on the fly after running the models. And this is using, well, I mean, this documentation was human-made, but is assembled when the model is computed, and is also including maps and references and everything. So for the, just to answer to these questions, but for both models, so the pollination model is largely based on this publication from the JRC, it's Estimap. While the IPCC methodology for carbon is largely based on this publication, the new IPCC Tier 1 Global Biomass Carbon Map for year 2000. And one thing that you might have noticed is that the report basically is assembled and changes on the fly while I add more queries. So now, for example, I'm showing you the report. There are the sections on pollination and carbon. But let's try, for example, to run also the recreation one. This model takes a little bit of more time, but let's see. I mean, I'm using a quite coarse resolution, as you see, so the models are going quite fast. So the data flow now becomes huge because we have the pollination part here, the vegetation part here, and this is the recreation part. So the recreation part is what is looking at many things of, let's say, attractiveness features from the environment, from the landscape, and also on the presence of users, recreational users, mainly the population in the cities. So you can see I can zoom in, zoom out, I can basically interrogate this data flow, and I can click on each of these boxes so that I know exactly how the information is produced. Like, for example, the solar radiation for the pollination part is coming from this layer, and this layer is originated by WorldClim and is giving the solar radiation, the average between 1970 and 2000. And if I want, I can also go to the website and check that. So it's completely documented both in the data flow and in the report. So the report is a bit different because it's using a narrative format and is more like a paper, let's say a scientific article, or with the classical sections on introduction, methodology, maps, annexes. So system is, for example, at this stage, I know what is the supply side of the recreation model. This is a model, again, it's an indicator from 0 to 1 saying how attractive is the landscape from a recreational perspective. And mind that I'm talking about recreation here and not tourism, because this model is meant to capture daily trips, daily-based recreation rather than touristic flows. And when the system, when this model will be completely observed, okay, so this is the supply part, but this is also taking into account the presence of recreational users. So as you see, the area around Rennes becomes more important, and also the area around, I don't know which city is this one, Le Mans. Why? Because basically the closer is a recreational site to the population, and the more likelihood is that the recreational users will go to this site. And the report now includes, as you see, has changed, and there is also the documentation about the recreation model. Also, the recreation model is largely based on the work of JRC estimate. So what is the take-home message of all of this? That we have this palette of predefined queries. These predefined queries are, let's say, more complicated models, but the technology and the philosophy is basically the same that what I was showing at the beginning. So very simple, semantic, concept-driven searches here that are connected to a web of knowledge and artificial intelligence that allows to responding to these queries using semantics and assembling the right informational artifacts for the right queries. This palette of ecosystem services related queries is available for every user. So anybody that registers as a user can go anywhere in the world without providing any data, will be able to perform these queries and get a default, let's say, an answer using the default global data available. In a more advanced way of using the system, I will show you later, you can include your own data, tag it semantically, so the system knows that also the local data becomes part of the knowledge base. And then the system is smart and will be able to pick your own data while resolving the same kind of queries. I don't know if there are more questions at this point. I think
not yet.
Okay, perfect. Thank you, Thomas, for giving me some feedback here. I feel very I feel very alone with my voice. Okay, so I think I showed you the Explorer generic views. I show you the ecosystem services palette with the predefined queries. Now I want to basically stress the fact that this technology is completely generic, so it's not meant to resolve only ecosystem services related problems. Okay, we have, let's say, the generic way of using the search bar, which is this one. You can type stuff in the search bar and hopefully you get an answer. You can press the space bar and get the predefined queries. Now we are working on delivering more, let's say, thematically customized user interfaces. And in particular, we have been working in the last months with the United Nations Statistical Office for an application dedicated to natural capital accounting. So what I'm showing now is not completely available to everybody. You can make a request in the profile management part of the website. But because I am a special user, I didn't show you this part. So if you go to the bottom right, you have all the information related to your user. Please forget about my email. And so you see that basically there are these icons. These icons are the same ones that you should see in the control center here when you start the system from the control center. And because I'm a special user and I'm in the natural capital accounting group, so I have this app available. So I can click on it and see what happens. Okay. So on the top of the generic user interface that we call K.Explorer, we can develop any kind of application that guides the user to produce more maps, more outputs of any kind, and not only maps. But for example, in the particular case of natural capital accounting, the main outputs are not maps, but tables. So natural capital accounting is about the change in the natural capital from one time step to another time step. And basically, we are trying to use the same, to match the same kind of usability with an application like this. So let me reset the system. And for example, this is how to reset the context. And in the region of interest here, you see you have where and when. So right now I'm using the map boundaries. So the context is set according to where I am in the map. But if I do this administrative region, so this side administrative region, then the map becomes alive and starts suggesting me possible administrative cases, administrative regions for the analysis. And as I zoom in and zoom out, these are changing. Now, this is, for example, the same that I was using before. E let belong. So let's say I want to see the ecosystem extent account for this particular region. So I will explain about all this section later, but very quickly. Administrative region, this is the spatial resolution. This is the beginning and this is the end. So my analysis will start in 2010 and end in 2019. So let's do the ecosystem account analysis. I click on these three dots and I have different options. Ecosystem change summary. This is the simplest table. I just click on it and then the system starts calculating. So natural capital accounting, as I was saying, is about the change in natural capital. And you have this kind of changes. You have, let's say, you have thematic chapters in natural capital accounting. The first one, ecosystem accounts, is how much of a certain ecosystem is available in a certain moment of time and how much is changing over time. So this is what we are doing now. Condition is about how healthy is the ecosystem that we are analyzing. So, for example, for this particular app, we are doing, we have provided some solution for forest conditions. I'm not going to show them now. Then you can basically assess how the ecosystem services quantified in biophysical terms are changing over time, and also their monetary value change over time. So I decided to show you only the ecosystem extent part. So this model is, first of all, is establishing the ecosystem types. And this is using the IUCN methodology. I will show you later in the documentation part. It's quite coarse in the region. You don't have many ecosystems, but well, the majority one, the major one is cropland. Then you have urban ecosystem. Then you have temperate forest. Then probably something related to water. Yes. So ecosystem, the ecosystem is classified. Ecosystem type is classified, but it's classified over time using these variables. So the land cover type, the mean annual temperature, the elevation aridity index, if the system is mountainous or not, and the temperature, and is quantified in terms of extents. So exactly what I was saying, every ecosystem type is measured in terms of area, square kilometers, in 2010 and in 2090. And the change is, the net change is computed in this table. So all of this was done automatically just by selecting a context of analysis, the time, the temporal and the spatial resolution, and then basically clicking ecosystem change summary. And this produces, instead of the tables that we have seen before, we also produces the table, the maps that we have seen before, but also produces a table that can be exported in an Excel spreadsheet. I need to take a sip of water, sorry, Excel causing problems. So this is the table exported in Excel with all the ecosystem types that have been identified, their special extent, and they change between the two years of analysis. I can close this. Now let me show you the report. There is a little bit of introduction about the SIA framework, which is the System of Environmental Economic Accounting. This is the standardized way approved by the UN on how to do natural capital accounting. Then there is one part explaining ecosystem extents. In this particular methodology, we are identifying ecosystems based on land cover, aridity, mean annual temperature, type of landform, elevation, and this is the output, the ecosystem type. So this methodology is not invented by us, but is taken from the IUCN global ecosystem typology. And indeed, if you have seen the table itself, it's also saying that this typology is based on the level 3 of the IUCN global ecosystem typology. So I am producing not only maps over time, because obviously, as I said, I mean, the system is knows the context, and the context is the windows through which you are looking at the world. The scale is important, and temporal part is important, and also the spatial part is important. So I have the spatial resolution here, and the temporal resolution here and here. The same, I can do exactly the same for land cover, for example. This is should be a bit fast because the land cover has been analyzed, but land cover, as you see, is giving you a little bit of information there on land cover. So basically, the system will compute the same ecosystem change, but for land cover. Okay, I think I did something wrong at this point. But this is the idea that I wanted to pass on, is that we have a generic user interface, and then we can provide applications, thematic applications on the top of it that are devoted to resolve particular specific queries, like, for example, in this case, those related to natural capital accounting. So I covered the part on the palette, the SIA application. So now I would like to start with the modeler, which is a little bit more advanced. Please let me know if there are questions on this part. I can stop here. I'm actually exiting now the online engine, because what I'm going to present from now on requires the software download. So remember that we were here. I had started the engine, and if I click on this, basically I can access the same K-Explorer user interface. Again, just to repeat a little bit, I can start typing with uppercase. The system will suggest possible administrative regions. In this case, should go to Sardinia. Okay, now I have it, and then I can do all the type of queries from elevation. I mean, I'm just showing elevation because it's very intuitive, but I could show you many of these variables. We have basically 200 global layers about any kind of variable. Okay, so Explorer from by clicking the globe icon in the bottom left part from the control center. Engine is on. Now I'm starting the modeler interface, and I'm going to show you a little bit of how to use the modeler. So the modeler is based on the well-established Eclipse IDE. It will start in a minute. We have a team of developers in BC3. Ferdinando is the lead developer. Then we have Enrico, we have Steven, and Andrea. Many Italians in the team. So this is how the modeler interface looks like. Actually, I like to. What I'm going to show you is a set of nitrate-related models that we have developed for the case study in France. But before that, I want to show you basically a little bit of this interface. It's a little bit more complicated than the other ones. Here basically is the interface that the modelers use to create new models or annotate data sources in a semantic way. So on the left side, you have the projects in which you are working. The first thing you would have to do as a new user is to create a new project. For example, I can create like a alice.winterschool. And it appears here when a new project is created is almost empty. So, for example, I need to create a new namespace to start adding my own code. Now, for example, I want to show you how to import your local data. So I'll just call it data. This is winterschool.data. Sorry, the other name was already existing. Okay, winterschool.data. You have the namespace here is empty. What you need to do in order, for example, to add your own data, I have prepared some data that are related to to river-related information for the Cusnon case study. So you have resources here, and you have some data that you want to use. In this particular case, I want to use these two TIFF files. One is about the temperature in the river reaches, and one is about the stream flow in the river reaches. So what I need to do is just to drag and drop the layer on the resource here. What happens when you do this operation is that the system ingests the information, the layer itself, runs a lot of tests in order to understand what the information looks like. You have this resource editor that appears when you left click on the resource. Basically, the system has identified also where the information is located. I can give them more information in this resource editor. For example, I can set the time of this information. This is for 2018. You can just save. Okay, what happens is that I have this layer in under resources here. And so far, we have introduced non-semantic information in the system. Now, in order for the system to understand that this information is part of the semantic knowledge base, I need to annotate this layer semantically. So the way to do it is to connect this layer with its own URN. I copy the URN, so I right-click on the layer and then copy URN. Then I go here, and then I write model. This is the universal keyword for starting a model in our system. This is the URN itself. And this information is related to temperature. So as now I'm writing, and then I will explain why I'm writing this. UPAC water. IM temperature. So off Earth reach. This is also during summer. So in the 3 warm months. And this is the unit of measurement. Now I end the modeling statement with a semicolon, and I Control S, and then I save the information here. Now, if you go here, you have water temperature. So what I've been doing is basically to connect a resource identified with a URN with an ontology related to that. And this ontology basically says that this is the temperature of the water in the river reach during the summer months. And this temperature is measured in Celsius. So this language that you are seeing here is called KIM, stands for Knowledge Integrated Modeling, and is a declarative language that we have developed in order to do semantic modeling. And as a grammar that is very similar to English and reads like English. This is very readable, as you can see. So model this particular resource as water temperature of reach during summer in Celsius. Now, why is written like this? First of all, everything that has to do with chemistry is related to the UPAC authority. So this basically allows us to not contain all the taxonomies and identities that are present in other dictionaries or tesoros. In this particular case, we are referring to UPAC for everything that is related to chemistry. So that's why we write UPAC and water. Then IM temperature is, let's say that this part here is the namespace that contains the concept. The concept itself is temperature, but I will show you later how to import the knowledge base. And this is the generic namespace that contains the concept of temperature. Reach is the river reach, but is contained in the namespace named Earth. And the same goes for summer. So I will show you this in a minute. Now, it's very likely that when you do an annotation like this, the engine is not completely synchronized with the modeler. So I have prepared this already before. And I was telling you that basically this information is constrained to the case study in France. So I opened the Explorer. The Explorer is like this. I was in Sardinia. I need to reset the context. And I reset the context. Then I go to the French context. This is the French context is declared in the same language using the WKT coordinates. Here I'm also specifying, for example, the spatial resolution and temporal resolution. So this is our case study in France. And the information that I have just annotated is water temperature. I drag and drop it on the system, on the target here. And this is now available in my context of analysis. So the water temperature goes from 16 degrees, 16.2 16.01 to 16.6. And I can zoom in, zoom out, click on the points, and see the values. So this example is to show you how to annotate local information semantically. I have done the same, for example, for stream flow here. So the stream flow goes from 0 millimeters to 3 millimeters, more or less. And if I click in the data flow, I can actually see that this raster resource is exactly the TIFF file that I have imported. You can see it here. Current flow sum.tiff. And right, this is basically everything you need to know about how to import local knowledge. So you can drag and drop your information layers here, and then you use the URN in the namespace, and you link the URN to a concept using the KIM language.
Stefano,
Any question? Yes.
Yes, there is a question from Benjamin. Can we share data with others by dragging and dropping our data in the engine?
Yeah, good question. So the way I was exactly going there. So the way to make your own data available to the public, or you can also be, let's say, a reduced set of users is also possible, not entirely public, but available. Is basically, remember that you have a resource, like, for example, this one is Streamflow. You click on it, and then you have the resource editor. And then you have a button here called Publish, and you click on it, and then you have basically a guided way to publish this information. So this is technically possible, and it's already available. The only issue is that so far we are the only one having our nodes in the system. So we will be hosting the data if you publish it this way, which is totally fine. I mean, we are happy to receive data from all the users. But you need to understand that basically what we are trying to build here is a Wikipedia-like model for doing integrated modeling. And so part of our strategy is to include more and more nodes in the network, so that we have institutions completely dedicated to, for example, data management, and because I mean there is a lot of work involved in keeping the data in well shape, and we hope to have authorities for data very soon. We are already working with many institutions, ISPRA in Italy, SANBI in South Africa. I mean, these are institutions that they have data in their DNA, and we hope to include them in our partnership. Any other question related to that, or other questions?
Not yet, but Benjamin is answering that it is great, really great.
Thank you, Benjamin. Okay, yeah. I'm going a bit all over the place here with this presentation, but I think it's okay. So now what I want to show you, so I showed you the creation of a local project. I show you how to import your own local data and to tag it semantically. Yes, now I need to show you that basically everything that we are doing, all the projects that we work on, including the source code for the entire system, is hosted in open online repositories. So if you go to bitbucket.org, which is something similar to GitHub, if you're more familiar with GitHub, this is Bitbucket, this is by Atlassian. We are using all the Atlassian suite for this project. So you have the k.LAB project is the source code for all the software stack. And but also there are also all the projects, so the projects written in Kim, which contain the models and the data annotations for everything that we have been working on in the past. So for example, if you click on projects, you have the Alice folder. Under the Alice folder, you have all the Alice related projects. So this is for the French case study, for the Irish case study, for the Portuguese case study, and for the Spanish case study. If you want to import this project in the modeler, the way to do it is to do this procedure: file, import. Then you have two choices: is projects from Git. So I want to import it from Git. This Git project could be in my local repository, and I will do an example later, or in an online repository. In this particular case, this is in an online repository. So I'm going to clone URI. Now I need to here copy and paste the address of the repository that I want to import. If it's the French, for example, case study, I just go here, I click on clone, I copy, and then I go here and I Control V. And in this way, I start the procedure to import the project. I have already done it here, so I won't go until the end of this procedure. And when I'm done, I'm actually having the entire project in my workspace here. And I can observe all the models that are available in the project. So you see, I mean, we will talk maybe more about this later on, but we have models about pretty much everything in the Alice project, from fire, ignition, to recreation, to water quality. I want to show you a couple of examples about water quality. Very fast, because I don't have much time. So I reset the context. I observe the context of analysis for the French case study. Just to double check I am here. Okay, perfect. Then I have some examples about nitrates. So this model is about nitrate load. I can just drag and drop it, and I want to show you how the model is written. So this model is modeling the nitrate load. So this is the non-semantic name, nitrate load. This is the way we express it in semantic terms. It is the ratio of nitrate mass on the watershed area. And this model is observing as input the area of the subcatchment, the proportion of broadleaf forest in the area of the subcatchment, and the percentage of surface occupied by broadleaf forest within a 200 buffer in the adjacent hill slopes. This is the riparian broadleaf forest proportion area of watershed. And how do we combine these three outputs? We combine these three outputs using this particular resource. And this is something that I want to show you. First, let's see. The output is here. So we have the nitrate load in kilograms. It goes from 25,000 to 125,000, more or less. The majority of the observation is between 75 and 85. K. And as I said, you can observe, click, see the histogram, click on the points, see the values. Okay, so how was this model developed? So as I said, I'm using this URN. So this URN is actually pointing to a resource that is here in among my resources. So this is called BNNO3 low. BNNO3 low. This is the resource. I left click on it, and then I have the resource editor open. So this is telling me that this resource is a classifier. So this is actually a machine learned model. In particular, is a Bayesian classifier, and uses as input the three inputs that I was showing you before, the area of the watershed, and so on. If I want to see this model, this machine learned model, I can actually export it. So I right click on it, I can export the resource. And this is, for example, you can export it in many outputs, but let's say, let's export it as a BIF file. BIF file is basically a network file, Bayesian network file. I can open it with the system that we used to create it. So this is the Bayesian net editor in Weka. I can open and go to Winter School. This is the BIF file. This one. Okay, so I need to lay out a little bit. So the output is nitrate load. The inputs are the area of watershed, the broadleaf forest proportion, and the riparian broadleaf forest proportion. And you can, I don't know if you know about Bayesian networks, but basically it's a directed acyclic graph with computational, with probability tables attached to them. And I can see the probability table here for this particular node. Now, this is not very easy to navigate the Weka editor. So that's why I want to also open it with a text editor. So file, open file. One sec. Yes, so the idea is that what it is, it's basically a combination of states for each given node and the output node. So the output node is the nitrate load, and the input nodes are these nodes, and then you have all the probabilities that link every class, every interval of this, of every node. So you have, for example, 3 intervals in each node, and all the possible combinations are matched with a possible probability here. This model was developed with data. So what we did was that we used a database, a large database from the institute, Hydraulic Institute in Cantabria. And we used Weka as an engine to do the machine learning part. So all the machine learning components in the system are deferred to the Weka system, which is completely included in the system. And there you have tons of possible classifiers that you can use. We like a lot to use Bayesian network because they are not complete black box. so you can also navigate the structure of the model that is created. I want to show you very quickly how a machine learning model is created. So I had done this before, just to give you an idea. Let me see if I need to reset the context. This is a learning test case that I was running before. This is within the case study of Spain. And this is the model that I'm going to launch now, and it's going to run on the fly while we speak. So I will be learning the land cover type based on 4 predictors: the distance to the coastline, the slope, the elevation, and aspect. I mean, the list of predictors is very limited and is not typically what I would do, but this is done just for explanatory purposes. So learner, just drag and drop it here. So what is important to notice is that instead of the model keyword, which would be, for example, used to show you the land cover data, so the land cover data is annotated in this way. It's modeled, the ULN, as land cover type, and then is classified into, and then you have the different kind of land cover classifications. Now, the system here is actually learning using a Weka BaseNet classifier, is learning the land cover type, which is being provided by our case study partners, IHC Cantabria, and using all the predictors that I was explaining from. So what we did was to learn land cover type, which is this one. I'm running at a coarse resolution just because I want to make a fast computation. I could do this at 50 meters, at 10 meters if I have time. Just taking it a little bit more time. So I'm learning the land cover type based on the distance to coastline. All of this has been computed on the fly. Slope is coming through a WCS service, elevation WCS service, aspect also WCS. All of these, they have been used as predictors to learn land cover. And this is the output. So the output obviously is not going to be amazing, but what you have is in the report, you have exactly how precise was the model in learning the land cover type. And this is the typical statistics for a machine learning model. This is the confusion matrix. So you see that, for example, I think coniferous forests are completely missed, and agricultural vegetation also are missed. But it's just to give you an idea that the system is able to learn a variable using predictor variables. While this, for example, would be the case study in Spain. So, I mean, ultimately, we didn't use our modeling routine for land cover change within k.LAB. So this work was done by Thomas Group. But this could be totally feasible in the system, within the system. And this is land cover type at this coarse resolution, 150 meters. Okay, so it's 20 to 5. I think I covered more or less what I wanted to cover. I think it was a bit challenging because this, let's say in general, the software stack, as you see from this slide, is quite distributed, and there are many pieces to explain. I have been able to explain quite well, I think, the Explorer part and its applications. I went a little bit through the modeler, which is the entry point for people that want to contribute data and models. And this part is the part that you don't actually see because it's constituting the semantic web itself. So the engine, you see it because you need it as an entry point to the semantic web. These are the nodes of the net that are serving data. And these are the nodes of the net that are authenticating the users and managing basic data privacy and all that part. Yes, the idea is that basically with Alice, I just gave a very little example about nitrate load. Well, I could continue a little bit because with that part on nitrate was quite interesting as we work with Thomas to make it as calibrated as possible. So, okay, I'm in the Explorer. I observe the case study. And then I can drop model after model. So the load, for example, can be converted into concentration. So this is the load as before. Observing the three main inputs and then giving you. Yes?
Stefano, there is another question. Do you have example of the time required to run models depending on the resolution and the number of the data layers?
Yes. I mean, if we are talking about the models that we have made available already, it really depends on the context that you are analyzing. I mean, you can go from 20,000 pixels to 50,000 pixels. Actually, with this online engine, you have the power to break our system, because if you zoom out and you make a query for elevation for the entire world, the system will try to give you an answer with probably, I don't know, 50,000 million pixels. And so this, I mean, obviously the engine that we are providing online is a powerful machine that is giving you answer in the fastest way possible. But otherwise, if you're using the software download version, so the control center, the engine runs in your machine, and that is basically using the computational power of your machine. So that depends a lot on the quality of your machine. But I mean, the answer is it can take up to 6 hours to run, for example, a complex model like recreation for an entire continent, which is not bad. I mean,
I think, okay, there is another question, like a practical example from Marie, but maybe you can just finish your example for the Quenon River on the nitrates issue. And then she's asking if it is possible to show an example about how to copy and paste an existing model and to use our own land user or land cover map data.
Yes, sure.
Because I think that people are quite interesting to maybe replicate or apply the existing model of k.LAB, but adapt that to their case study with their own data set.
Yes. So first of all, let me finish the models on nitrate. So this is the calibrated nitrate concentration, and this is, after that, I will show you the level of. Actually, Thomas, you can explain the output of this much better than me.
Yeah, I will support you, don't worry.
Okay, so this is the initial model that we ran before. I was showing you that, and this is basically a Bayesian network model. Now we convert the nitrate load into nitrate concentration here, using this particular algorithm. So this is the way to define an algorithm with two inputs, stream flow and the load. Now, because that load was not taking into account the agricultural area, which is quite important, we have made a modified version of it. We call it calibrated nitrate concentration. And this is taking into account basically the fertilizer coming from the maize crop fields. And because in France you have this regulation that tells you basically the traffic light, you know, it's under 25, under 25 is low, between 25 and 50 is moderate, and above 50 is high. We made a model that basically is taking the output of this and assigning a red and orange and yellow, sorry, and a green color to these three classes. And I think it was already done, but it was here. Okay. So this is the level itself. As I was telling you before, I mean, this map in the background, you can change it from all of them. You can also decide to not have it in the background. And in this particular case, to see the traffic light colors, for me, is much better to not have it. So in the red parts, you have these areas that are above the critical threshold. Then you have the yellow areas in a so-so situation, and then the green areas that is green light. Thomas, do you want to say something about this?
Or maybe just to complete that, basically we use a model of nitrate concentration that has been developed from the Cantabria team, that has been applied and tested over the Spanish region. And one of the main predictors was the proportion of forest, because they have very low concentration of nitrates in the flow. Of course, it was not representative of intensive agricultural area, so we adapt this model by using the proportion of crops within this. Okay, sorry, I will start my video. Okay, so we adapt this model by just replacing the proportion of forest by the proportion of cropland within the area that is contributing to each part of the stream here, and we compare this result with current observation of nitrate loads and nitrate concentration, and I would say that it is pretty good, but it means that obviously it does not take into account all the farmer practices that could be particular from one place to another. But basically, I think we exactly recognize which stream are in the worst case situation and which one are in the best situation. So we are pretty happy with these results.
Great. Okay, then I need to answer to the question about land cover, how to annotate it. And I have an example here, for example, in Alice's test. So this is the land cover TIFF information coming from Cantabria. I just import the TIFF file, as I was showing you, from my folder to the resources. I just drag and drop it. And then the way to annotate it is this one. So model, and then the URN, calling the non-semantic resource. This is basically the TIFF file. Now I need to tell the system that this information is land cover type, and this is how you do it, as land cover type. But because land cover type is not a numerical variable, is a classification, then I need to match all the codes that are in the TIFF file with a concept, and the concept are the land cover classes. So in the particular case of the Spanish case study, but also I think we use the same land cover classes in all the case studies of the ALICE project. So it's broadleaf, coniferous, shrubland, grassland, agricultural vegetation, bare area, artificial surface, and water body. With this simple way, when I'm in a context that is Spain, sorry, let me go to that with the minimal. So I can go, for example, I can go to the Spanish case study and check for, so this is partly the land cover, the Spanish case study, and partly not. I type land cover type here. And now we will see that the system will obviously try to resolve my query with the best available information. And as you see, it was partly taken with the Corinne land cover that is available at the global, at the European level, and partly using the data that I have fed to the system. So you will see something very strange here, where basically you have Corinne outside the case study, and then let's say the ALICE land cover classification inside the case study. This is just a way to show you that the system is smart and can resolve queries according to the knowledge available in the system. I hope this was clear enough as an answer. And once you have made available your land cover information to the system, then because it's local specific, it will likely have priority on all the other information. So it will feed all the models based on land cover. And mainly the ecosystem services models that I've been showing at the beginning, they are largely based on land cover classification. So you can affect the models there, for example. I think I'm finished, and I'm very happy to take more questions. Or if you want, Thomas, we can discuss a little bit the generic implications for the ALICE project that we wanted to make clear to the audience.
There is one technical question before maybe to do so. Benjamin, still the same. Looks very interested. Is asking that as in air, can we launch k.LAB several times simultaneously on the same computer to test several simulations at the same time to save time?
Yeah, I mean, the computations run in parallel. So you can, when you're using, let's say, the engine from your own machine, you can run multiple models at the same time. You don't have to wait for results in order to launch the next one. So you can save time there. Then if you have really big, let's say, queries and analysis, and you need to do a routine kind of analysis on, in a repetitive way, then you need to, I mean, there are ways to write a script that does this for you, like you do it in R, basically. But this is a quite advanced way of using the system. And if you want to do that, I mean, please contact us at support, and then we will try to support you.
Mary, that was asking the previous question, she's really happy about your answer, and she thinks that k.LAB is awesome.
Okay. I mean, the philosophy of k.LAB is, as I was telling you, it was born for ecosystem services, but we realized through time that this can be applied to a whole bunch of modeling problems. And it's the philosophy behind is basically to make what Wikipedia has done for encyclopedias. We want to do it for modeling in general, to join the information, to integrate the information that is out there, and to involve partners that are willing to cooperate, and to make it as open and as accessible as possible, so that the world can make smarter decisions, sustainable decisions with better information.
Okay, and so I have maybe one or two questions more related to maybe the perspective of k.LAB. We have seen this morning that most of the land cover or the inputs that you are using come from derived satellite-based imageries. And because satellite images are also data that are provided by any kind of data provider that could be requested with WCS services. Do you think that there could be this kind of maybe land cover automated classification based on, I would say, live stream satellite images from Sentinel-2 or Sentinel-1 as well?
Yes, it's totally feasible. On the technical level, there is no doubt about how to do it anymore. So we know that it's feasible and we know how to do it. The only issue is to have all the relevant partners in the same room and willing to cooperate. But we are talking with the European Spatial Agency. We are talking with NASA as well. And we hope to have this on the fly, and let's say, queries to the satellites available soon. We have a demo already about that, but nothing that we can actually offer to the users at the moment.
And in ALICE, finally, we did not integrate everything into k.LAB because we were not into that at the very beginning. But I think that now the attendees can consider that it is completely feasible to integrate all this habitat mapping, maybe connectivity mapping, and of course ecosystem services, maybe in few months or few years, if you do collaborate to k.LAB. But well, I think that it is also obvious that we need scientists like Jose this morning in order to better translate all these requirements in terms of in situ field work, in order to better define what are the land cover types, suitability maps, all these prediction models and so on. But I think it is a great way to have more generosity and replicability in all these scientific projects as well. I don't know if you have other questions, all of you. Maybe also I can ask to Jose and Hugues to be part of this discussion now, because it is, I think, quite open. I don't know if they are still there. Yes, they are.
Yeah. Hello.
But I think it is good to have a broader view with what are your feelings, maybe what are your reflections based on this presentation today.
Yeah, thank you. Yes, I think the storytelling has been, from my point of view, successful to show that, to demonstrate that we can manage our own data, to be each time more and more objective in the conclusions that we get. And this presentation that Stefano made is like the final step of integration information. But I think that, or no, I think is that was we have been done in ALICE. We use the in situ information, satellites, and multidisciplinary teams for understanding reality, for understanding how landscape change, evolve, function, and so on. And finally, once the information has been worked, has been clear, discussed among experts and scientists, these kind of approaches allow us to integrate everything, to communicate the information from the river ecology with landscape dynamics, with vegetation patterns, to put everything in common for running with the same algorithms, information for different case studies, for different time periods, and finally getting information from ecosystem services and different applications. So, well, I think we try to demonstrate how to integrate information with different platforms, and these final capabilities of ARIES and k.LAB World Integrated Modeling Community that Stefano showed is like something important to have in mind to any scientist and data manager to know that there is a technology over there that can integrate everything that we think correctly into a common world that will allow us giving integrated conclusions.
Yeah, I mean, the ALICE project was ambitious in many ways. If I could show you the list of models that are implemented, it's humongous, and there are still many that we are missing. I mean, we weren't able to completely integrate the hydrological parts. So, for example, that's why you have stream flow coming as an input. So it's loosely coupled from an hydrological model. Same goes for a water temperature model. So these two parts are the parts that we are still missing and require a little bit of additional work in order to integrate the full computational chain in k.LAB. But I think nevertheless we were able to present the case for basically showing the added value of this methodology of integration in general for solving real world problems, which is the main issue with an INRAe project, because we need to remember that the INRAe projects are not for pure research. They are for being applied in the domain of cooperation and solving real world problems.
Yeah, but there is no solution if there is no research behind. So in ALICE, all of us know that we have been discussing quite a lot of people from the different institutions to have some clear conclusions that were included afterwards in the k.LAB platform for modeling ecosystem services related to that patterns, that functions, and so on. So we have to know what are we talking about, research, for then apply into sustainable solutions.
Yeah, and I think the world needs science today more than any time in history. And having good science in the background of any decision taken, I think, is a good starting point.
Right. Okay. Just trying to. I don't know if there are any other questions. I'm just trying to move my window. Okay, it's getting better. Well, I think at least two people are quite really interested by what have been shown today and this afternoon. In terms of short statistic, we start with 90 people, but we lose approximately half of people during the day, and it's getting late now. But it's not a bad score, I would say, because at the very beginning, when we talked about organizing this winter school, we were hoping something like 20 to 30 people, and finally the COVID has allowed us to be with almost 60 to 70 people this afternoon. So would like to thank you, all of you, to be part of it. And just maybe to finish with few slides in order to conclude this winter school. Okay, I start this slide about this, like, first very simple illustration about what is the landscape. And of course, it is something that is very complex, with a lot of interaction between humans and natural processes. And we try to define and to show some methods in order to characterize this landscape as habitats, as functions in terms of connectivity, and in terms of ecosystem services. So I think that the example provided by Jose, Hugues, and Stefano were quite enlightening what could be done, but of course we were not exhaustive. And I would like to just open the discussion, or maybe open your mind about the fact that landscape are, of course, dynamics. This has been mentioned several times during the day, but of course there are several processes that could make the landscape evolving past or not, but there are, of course, anthropogenic disturbances like pastoral fires. There are some kind of legacies in terms of past practices. There are natural processes like encroachment or grazing, meaning that I think we should more take into account this kind of landscape dynamics into our assessment. It means that if we want to have maybe more impact towards decision makers and policies, we should better anticipate these changes into the future in order to define sustainable strategies. It would mean that we are able now with this kind of tool to maybe better estimate what would be the trade-off between the gain, the trade-off, the gains, the losses between ecosystem services, habitats, and functionalities by exploring the future. So this is just a way of maybe make a small reminder about what was the philosophy of ALICE. Basically, it was to develop this kind of tools, but also to explore the future based on what if there is no B genes and what if there are B genes, and what do we gain in terms of ecosystem services, or what we're going to lose in the future based on this kind of very simple scenario comparison between business as usual scenario or a B gene scenario. The idea is just to explore the future based on different type of scenario and to apply all these tools in order to make more profitable trade-off analysis between biodiversity, economy, or any kind of environmental assessment. And if you are interested in exploring this part of the landscape dynamics, I would invite you to be part of another seminary, another day of conferences tomorrow. And we have invited Peter Verberg, which is quite a very famous scientist in all the land change science community. And he will talk about the landscape changes and the land use modeling at the global scale. And its implication in terms of ecosystem services. I will make a kind of short review on what could be done at very fine scale in terms of land use and land cover change modeling as well. And Gaëtan Palka will present you one of the model of the land use and land cover change simulation we have developed within ALICE in order to present you what could be done at a very fine scale that is completely compatible with everything that has been shown today in terms of environmental assessment. So you have the link of the web page where you can find the Zoom link to access this seminary tomorrow morning. And for those that are interested in participating to a more participatory science workshop, there is a workshop in French in the afternoon that will be dedicated to present all this scenario and all this environmental assessment. But of course, it will be in French, unfortunately for all you guys. So I'd just like maybe to thank you all to participate to this journey. And if José, Hugues, or Stefano, you have final words, I will be happy to give you the floor. And I just wish you a good day to all of you.
Yes, maybe I can begin. So thank you, Thomas. Thank you all for inviting me. And I think the main there are two issues for the future for us, because landscape are again going worse and worse because of human forces, because of climate, because of many things. And we will see that the more we are integrated the things and scenes in such models, the more complex the whole model is. So I think the first issue is to be, yes, complex but simple at the end when we propose tools to be available for a planner, for researcher, and so on. So it's the first. I think it's the first main issue we have to focus. And the second one is to continue to develop new concepts and to not be afraid to test new things and to be able to incorporate it on such models. So it will be more and more complex, of course, but I think we are going on the good way, but it will be a bit difficult, and it will be very soon if we want to make something change for real.
Yeah, me only adding just some words about what we tried presenting this morning. With a lot of information, speaking very quickly, I cannot go more slowly, sorry. But what we wanted to translate is that we want to put everything on the table to disentangle the complex patterns, processes, drivers of reality, dealing with complex landscapes, not only using the really available information, but going in detail into multispectral time series of satellite imagery, hyperspectral LiDAR, and everything that can be handled, the drones as Thomas uses, and everything to disentangle reality and to have the capability of defining more simpler indicators or more simple indicators that that we can develop just making complex analysis for trying to put afterwards in this kind of integrated modeling approaches, as Stefano explained us, by avoiding using the complexity of data and methods, by creating something more simple that can be understood, that put into modeling frameworks that interconnect the different parts of reality. That was our idea, and that's what Alice tried to put in the table for all of you. And thank you very much. It was a pleasure to be here, and see you in the next. That will be more, I hope.
So thank you very much, Thomas, for organizing this. And it was a pleasure, obviously, to be in the Alice project. For me, an occasion to work with very good people in their own fields, land cover change, modeling, and remote sensing. I mean, you are very, very good in what you do. And for us, very stimulating, you know, to integrate all the possible modeling approaches. And there is a lot of work for us to do to involve the broader community and to deliver the technology in an easy way. I mean, it's challenging even to communicate it to the broader public. And so an occasion like this is always a good test for me to test how the situation is out there, the modeling community and the non-modeling community.
Thank you, Stefano. Thank you, you guys. Well, I think that you said everything. I think it is important to share what has been done, and this winter school has been a great occasion to do so. I hope you will be inspired by what we have shown. Your comments seems to be in accordance with the statement. So now it's up to you guys. And finally, I would like just to thank you also, Mariana, for the technical support that she's behind that, everything, and all the colleagues that participated to this winter school. And I hope you will be able to meet each other soon as well, beyond the COVID situation. So take care of you and see you soon. Bye-bye.
Bye. Thank you.
Bye-bye. Thank you.
Bye. Thank you.
Bye.